Today we'll talk a little bit about text mining, as announced, as well as recurrent neural networks, and a bit about transformer networks as well. I know that last time I promised that I would make the dataset for assignment 4 available last week. The bad news is that gathering the data took me a little bit longer than expected, so sorry for that. The good news is that the data is finished being collected, and so later this evening the instructions for the assignment will be posted. So everything's been done for that. I just need to type out the instructions and post them on Toledo. Bit of news as always. Last time we already saw an article about the uncanny ability of O3 guessing where pictures were taken, and also this article goes a bit further in detail and also confirms that this model is in many cases able to beat master level GeoGuessr players. So also relates a little bit to the second assignment. So yeah, even large language models are getting better and better at this. So this is a professional GeoGuessr player who compares their results with what the model does, and he posts some pictures, like I'm zooming in on this bollard because I think that I can utilize this to identify where that a particular photograph was taken. Some people are also saying that it's not completely fair because O3 as a model can do or can perform web searches, which it sometimes uses to enhance its results or its predictions. Sometimes, or in many cases, in real GeoGuessr competitions, you're not allowed to perform web searches. You should do it just based on the picture. But still, that being said, the result is still quite impressive. You might also have heard that GPT-4o latest model exhibits large degrees of sycophancy, what basically means that it's a little bit too eager to congratulate you or to be positive about all the things that you're doing, even if you decide to chat with a model in a way which really reveals that that something weird is going on with you. It will basically still congratulate you and tell you that you're the smartest user that it has ever seen. So some people thought that this was a little bit annoying, and now also OpenAI have reacted to that, and they indeed say that they went a little bit too far in this, and they backrolled the latest 4o version, and they are now trying to prepare a new version where this is a little bit less pronounced. They also plan to give custom tools to end users to basically tune the level of sycophancy and other aspects that you want when you're conversing with ChatGPT. So nice here is that at least the reaction was relatively quick and that they're trying to do something about this. This is also pretty cool. There have been other models that do this as well, but again, this is a step further. Again, the idea here is that you enter a prompt and you get a complete 3D scene in seconds. So you can see a couple of examples here, like an underwater city, a broken down factory, a well-designed neat living room, and so on. Basically, if you would be planning to work on like some sort of VR game or something like that, this already looks quite convincing or can already get you a lot of the way there. It's not that the world is fully traversable, it's more like a 360 panorama type of picture that it generates, but still quite convincing, good results. So also interesting to see how quickly that these things are getting better in the time span of a year. A lot of LLM models, newer ones have been released as well. One noteworthy one, DeepSeek is working on their R2, which is also stated to be released relatively soon, but also Qwen, also coming from a Chinese company. A newer version of Qwen 3 has been released, which you can also download locally, and which gets also very impressive results for a model which is basically free to utilize, so the weights are open. So you can run it on your own machine, and on a lot of benchmarks gets very close to the state-of-the-art models that, for instance, OpenAI or Grok or Gemini or DeepSeek have been releasing. So also nice to see that competition is still going on there, and that things are still happening there as well. DeepSeek has also released a couple of interesting models, like one which is meant to perform or to produce math proofs. So they've also released that, but basically I want to avoid filling up the whole news section with like 10 new LLMs every week. Now another one which is interesting is that IBM has been working on crossing a state space model, an SSM, with a more traditional transformer-based model. The reason behind that being is that the transformer-based architecture has some benefits. One of the main benefits, and we'll also see that today, that it offers compared to recurrent neural networks is that you can do quite fast training. So you can train easier in parallel because you don't need to run through the whole input sequence, as we'll see. But there is a cost when you want to use these models to perform inference. And the cost scales exponentially in terms of the input sequence that you utilize for the model. So that's also why many of the still current models impose limitations in terms of the length of the input sequence, the prompt basically, or the conversation that you can give it. Nowadays, how people try to tackle this is by using modified versions of the attention mechanism, as we'll also see later on, where they perform some sort of caching mechanism, or they utilize things such as flash attention or sparse attention. But none of these are really perfect because you lose some detail, and that also makes models less capable to work with longer input sequences. They might start to forget things or not being able to recall very well from very long input sequences. So for already a couple of years, people have been saying that there is another type of model called a state space model, where people claim that it basically takes the best of both worlds, both worlds being the attention-based approach and the recurrent-based approach. A couple of such models have already been proposed with early claims saying that they are as promising as the attention-based architectures are, but none of the large AI companies have completely switched to such a model yet. So practically speaking, you should also wonder, okay, if this is like the next big thing, why is it still taking already more than a year and did no one really jump on this yet? Now, there is someone jumping on this. IBM claims that they have combined now a more traditional transformer-based architecture with a state space model. We'll see where this goes. IBM is IBM. They're not really at the forefront of current AI innovations, I should say. But maybe there is something in here. It will be interesting to monitor this and seeing whether these state space models will be adopted more frequently as well. We already saw a couple of weeks ago in another in the news section that also kind of this diffusion-based architecture where you try to combine block diffusion with text generative models, that this is another interesting avenue of perhaps getting a little bit more out of these architectures, but also this has not really become commonplace yet. So far, all of the companies are still sticking to kind of the proven pure attention-based approach, and then doing a lot in post-training with like RL from human feedback and things like that. But who's to say that this will not change at some point in the future? Okay, then it's time that we get started with talking a bit more about text mining, and first a bit the basics, but then also the recurrent neural networks and the attention-based approach. For the third assignment, as you know, you're kind of free to utilize like a small LLM locally if you think that would help you to make predictions. That might be cool to play with that. Other than that, you basically utilize pure Spark, as we have seen last time, and very likely you have been using TF-IDF-based features, or you've already looked that up a bit, and you have stuck that into a random forest or a logistic regression model. So we kind of start from there. You could call this the basic featureization approaches for text. And it's very similar as what we saw with images. So here too, you have kind of an era before deep learning and after deep learning. The era before deep learning was mainly geared in how do we come up with good feature vectors, vector representations for pieces of text, for documents, for even maybe individual words as well that we can then reason with, and approaches ranging from the ones that are a bit more manual in nature or very simple, just based on counting words or certain score-driven approaches, to already a bit more complex things that maybe use some early, smaller data-driven approaches with smaller neural networks, to all the way up until today, basically all that we were doing in NLP, such as topic modeling and position of speech tagging and named entity extraction. Companies such as NLT, or libraries such as NLTK, or companies such as Spacey, at some point or a couple of years ago, they were quite large in terms of offering solutions for that. If you would have to encounter this use case today where you say, okay, I'm getting legal texts and I need to extract monetary amounts and dates and company names and person names from there, nowadays very likely you would also just solve that problem by throwing an LLM on top of it with a good prompt. So also here you clearly see this difference between before deep learning and before LLMs, and then after deep learning and after language-based models. But still, for more kind of smaller use cases, it can be worthwhile that these kind of more basic featureization-based approaches are also explored, because then down the line you can stick those features in pipeline which is a bit more maintainable, at least like your TF-IDF features together with your random forest will not suddenly start to hallucinate, will also be way cheaper to run than even a small LLM model, even if it only has 7 billion parameters. So that's still where we get started from, but not going into like a lot of detail because today we also have stronger tools available there. So why text? Very often it's stated that if you wouldn't be looking at tabular data, and contrary to images, which we typically have a lot of, but still in a typical organization, if you really look at the majority of data that they have in a typical organization, will be text-based. If you look at claims or documents or emails or posts on social media or repair notes or customer support tickets or even internal documentation that you have, like websites or PDF files and what have you, all of that is basically text. Court decisions, legal documents, declarations, there is a lot of text in this world. And of course, a lot of text that's all being gobbled up today to train these large language models, but also perhaps that we can utilize to make some predictions on ourselves. Similar issue as with images though. Text in nature is rather unstructured, but I already said I don't really like those terms, unstructured, because in a way it's semi-structured. Of course, text has some structure, right? You can compose text in sentences, and sentences are decomposable into words or characters in some languages. There is a linguistic structure at play there. There is punctuation there as well. There are certain grammatical rules as well, but still it's meant for human consumption. These grammatical rules are not always perfect, or you have exceptions, or you have homonyms, or people misspell words and things like that. So it is a little bit less clean, let's say, or less ready for immediate use than your typical tabular feature matrix would be. So also here, like I said, we can split up approaches that we take to then extract some straightforward feature vector or some feature vector representation before and after deep learning. A lot of things that we do in machine learning is not so much, well, it is predicting, but to make good predictions, as we already have stated in a lot of cases, very often it boils down to being able to obtain a good representation for your data points, and a good representation in some pretty high dimensional space in a lot of cases, where you try to utilize that space as densely as possible. So basic approaches, yeah, easy. What can you do if you have like a collection of documents, or a corpus, as it's also then frequently called, with the plural being corpora, not corpuses, where each document is then composed out of individual words, you could say, or tokens. If you go a little bit deeper, you could even decide that you cut up your words into subtokens. That's also typically what these large language models will do, into fragments of characters, or even to the point of individual letters, also taking punctuation into account, and smileys that people have put in those documents into account as well. But basically every document is like a sequence of tokens or terms, or at an extreme case you could say, well, let's call them words, right, as your starting point. What is an instance? Typically a document forms an instance, but again, depending on the pre-processing approach that you want to take, you could decide, if that's easier for you, to first cut up your document on the level of sentences, and then considering every sentence as a particular instance. Especially at the early days of natural language processing, that was not so uncommon. If you think about something like a sentiment modeling, for instance, where you have a review that someone has made on a movie, and you want to figure out whether that user is happy about the movie or unhappy. Well, many models that we have, which are relatively simple, work quite well on the sentence level. If you have a full review, well, then you first split up that review into sentences. You calculate the sentiment score for each of the sentences individually, and then you just compound them by taking the average or something like that, and you report like a final score that way. So that's also frequently done. In any case, to do that, or if you want to utilize these documents or these sentences in some way, the end goal will in a lot of cases being, like I said, learning some form of representation, a real valued vector for each item in our set. So we're again going to embed our items in some sort of n-dimensional space. Like we already saw a little bit with t-SNE and UMAP, except there, we didn't, or with UMAP we kind of could make it supervised, but also here a question will be okay, but what's the downstream task? Probably the representations that you obtain for something completely unsupervised will be a bit different than if your end goal is making some predictions on this text, or if your end goal would be, I give you part of a sentence and now please, my dear LLM, complete the rest of the tokens that make up this sentence. So the representations internally might end up looking a bit different depending on the downstream task that you have. But okay, generally speaking, what's a very easy representation that you could come up with? This is basically the basic or the most simple approach, is kind of bag of words based approaches, where you just say, okay, I treat every document as a collection of these individual tokens, which might then be words, but could also be on the character level or the subword level, depending on what is your vocabulary of tokens that you want to work with. And other than that, we're going to ignore grammar and order and structure, and very often we will also ignore punctuation, although we don't really have to. We could also incorporate punctuation. And then we're just going to represent each Stardic document as, in this case, well, for every word that we have in our vocabulary, or for every token that we have in our vocabulary, does this document contain this token, yes or no? And then this is kind of a binary representation. From there, you can easily go to a term frequency matrix where, considering that the same word might appear multiple times in the same document, that you don't make this binary, but you put counts in there. And then once you have counts, you can normalize it by dividing by the max, and then you have something between 0 and 1. That's, of course, also oftentimes done. Then you have your normalized term frequency matrix. Okay, yeah, then the idea is that maybe for each of these documents, you also have some particular label that you want to predict. Positive, negative, neutral, let's say. You're doing multi-classification, then this term frequency matrix is something that you can immediately push into your favorite supervised predictive algorithm that's out there and see what it does. Drawback, well, of course, this is heavily dependent on the size of vocabulary that you work with. Effectively, you're creating a feature column for each token in your vocabulary, and you will have a lot of tokens in your vocabulary. So just out of the box, you will end up with about 20,000 to 40,000 columns. That's not going to work very well. This representation is also very sparse, obviously, because if you take like a vector representing one of your instances here, most of the entries will be 0, right? So that wouldn't really work well, but it's something that you could do. Maybe perhaps with a bit more pre-processing. Obviously, you can consider that for words that, well, you can if you get a list of stop words in the English language, for instance, then perhaps you realize that it doesn't make a lot of sense that you have a column for the words is and an and a and this. They're not going to be very informative. Probably every document is going to contain a couple of those words. So very likely you will decide that you kick them out, right? And likewise, maybe for words that would be very infrequent, although maybe a little bit more dangerous, because infrequency can maybe reveal some specific characteristic about the document that you're working with. But you could also say, well, if this is a word and it only shows up in like one of my 10,000 documents, it's not going to be very predictive, so I'm also going to kick out that column. And so from there, you try to reduce a little bit based on frequency, based on characteristics of the words that you have. You try to reduce the dimensionality of this vector a bit. You can then also play around with, okay, uppercase, lowercase, I'm not going to care. If it says this with an uppercase t or this with a lowercase t, I'm just going to consider that to be the same token. So that is also a way to reduce the number of columns that you have. And then you can also start to look a little bit more at the characteristics of specific languages. And of course, this differs depending on the language that you work with. But for English, for instance, you could say, well, I'm going to remove the suffix of words. I'm going to stem them. So I'm going to consider both the words jump and jumps and jumped and jumping. I'm all going to take that as being the same token, namely jump. And then again, you reduce the number of columns that you have. And you can also utilize lemmatization libraries to say, okay, better is kind of the same as good, so I will also consider this to be the same token, and flies and flight is the same as fly. So also you try to reduce the number of features that you effectively end up with. You can then try to enhance those tokens, because at the end of the day, like I said, you decide how you construct your vocabulary. You could also then take a part of speech tagging library that exists that does not just say what is the word in the sentence, but also what is the role of the word in this sentence. This is a verb and this is an adjective. And maybe you could couple that to the token itself, but then you're again increasing potentially the number of features that you have. So a lot here is related to not just taking the base term frequency matrix, but a lot of pre-processing that you would have to do on top of that as well. And stop words, remove those, or whatever language you can find list of stop words for most of the languages out there, and also try to take it that way. So okay, we're using bag of words with counts, word frequencies, bit better than binary. This is nice because at least it differentiates between how many times a word is being used across your documents. So you could also then call this the document term matrix. But there are, of course, a couple of issues by, again, even if you would do pre-processing and stemming and lemmatization and everything in lower caps and so on, there are a bit of underlying issues still at play as well. And one of the largest issues is what happens if your documents have differing lengths. Right? Then you end up with higher numbers simply because the document itself is longer and hence will contain more tokens, more words, without really being able to say that, well, the presence of these words in this document is then more important than other documents. So in some way, or probably it's also going to be a good idea that we will normalize based on the length of our documents as well to kind of bring that all to the same scale. We have a bit of a trade-off. We could just filter based on thresholds, on frequency-based thresholds. But on the other hand, like we want to find like a good middle ground between words which are not too common. So in other words, words that show up in all of the documents that we have, or most of the documents that we have, those are probably not going to be very interesting. Words that show up very infrequently, they're probably also not going to be very interesting. So we normalize our frequencies, dividing by the total of numbers of words in each document is a common taken approach. And also kind of a little side note here, but which is also easy to forget about, but this brings us back to week 1, basically. Everything we do here, remember that we're not just doing this for training in our training pipeline, but we have kind of the same thing going on when we encounter unseen documents as well, right? We will be able to execute the same pipeline that we have there. Okay, you could take that document, you know the list of tokens in your vocabulary, you count their number of times that they appear, and you divide by the length of that document. That all works on an instance-based level. There's nothing aggregated over different instances, so easy to be replicated on top of new unseen instances as well. But remember that new documents might have terms or tokens that you did not see in your training data set, for instance. And so then you should carefully consider, well, I'm not suddenly going to add new feature columns on my vector that I'm creating if I didn't see them in training. I effectively will have no other choice than to ignore them, also because my model during training didn't see those vector columns either. So again here, first train test split, and then think carefully about being able to replicate your pipeline on the test split as well, as always. Now, if we want to take this a step further, there is kind of an add-on technique that we can introduce based on the term frequency matrix. So the term frequency matrix we already kind of know. It's calculated per term, so per word or per token, and per document. And basically it's the number of times that the term appears in the document, which was our frequency, and we normalize it by dividing by the document length. So this is traditionally like a term frequency component that we utilize. And so far in the matrix that we built, we said, well, it's this thing that then creates the feature vector for each document by just going over every term that we have in our vocabulary. Now, to make this a little bit more intelligent, let's say, we can also consider, okay, but it's not just the frequency of a particular term in that document that plays a role. In a way, what we're trying to look for is we would also want to compare it with, but how common is this term in the whole corpus as a whole? Because if this is something that's maybe pretty rare in the document itself, but is even rarer in the rest of the corpus, I might still want to give that a higher kind of score or higher importance than maybe something which is very frequent in this particular document. But whatever other document I would take from my corpus, that term is also very frequent in those. Well, then I'm not really going to learn anything from that term. It's just always very frequent. So I would like to, let's say, downplay terms that are always very frequent or that always very infrequent. Those are the least interesting to me. So what I'm looking for is, you might be, or what I would like to see most, are terms that are frequent in this particular document that I'm looking at and are not frequent in other documents that I have in my corpus. And since this thing just looks document by document, this will not really give me that result. So what do? I calculate another component, which is called the inverse document frequency, or IDF component. And that one is also calculated per term t, but over the whole corpus C. So not a different IDF score for each document that I have in my corpus, just a single IDF score basically for each term that I have in my vocabulary, given a corpus as a whole. And this is calculated as, you have different instantiations, by the way, but this is one of them. They all typically include like a logarithm with a fraction, 1 plus the logarithm of the number of documents that you have in your corpus. So that's this length of this corpus C here, divided by the documents that contain the term. And what happens here is that as the number of documents that contain this term T increases, the IDF score basically becomes less and less. So what this is saying is that if you have a term that does not appear often in your documents, that it's going to get a high IDF score. And then basically you have the two things. You have both the TF score for a particular document, and it might say, well, this term here is a little bit frequent. It's not very frequent in this document, but it does, it does show up a couple of times. But I'm combining it, or I'm going to combine it with this IDF score, because if this is the only document in which this appears, I still want to boost up that score, basically. Well, how is this combination then done? Very simple. We just multiply both cases of them. So what this will do is this will give you a weight for each term that you have in each document. So at the end of the day, what you can utilize, or what this then being utilized for, is again, for every document, D1, D2, and so on, and for every term, you basically calculate a TF component multiplied by its IDF component, and you get a feature vector for each of your documents. The IDF is specific to a particular term, so this IDF component will be just the same for each of these feature vectors, but of course the term frequency component is specific also for each of the documents, so you will not end up with the same number at the end if you multiply TF with IDF for each of the terms in each of the documents. Again, think carefully about the train versus the test setting, right? So for TF, there it doesn't matter that much because this is instance-based anyway. If I get a new test instance tomorrow, the test one, to calculate the TF value of my T1, I just count the number of times that T1 occurs in the document and I divide it by the document length, right? I don't need to store anything. Well, I only need to know the way how that this TF value is calculated, but that's it. What do I utilize for the IDF value, however? Well, I don't have a new corpus that I could calculate the IDF value on. I just have a single test instance that this thing needs to be repeatable on, right? That's exactly the reason or the point between making a train set and then test instances, right? Well, you use the stored IDF value that you had for this term back when you trained your model. So effectively, these IDF values have become part of your model parameters, basically, of your model's parameters, or the parameters of your whole pipeline. So the corpus that's being used here to calculate these IDF values is, of course, the training corpus, and then these values are stored and kept to apply them on test instances as well. So again, if you have a new term in your test instance that you didn't recognize or is not a part of your train vocabulary, that would just get skipped, right? You can't include that in the feature vector that you construct for your test instances. Now still, even if you get this, you would still have to think a little bit carefully about, well, your dimensionality in terms of the size of your vocabulary. So still you would have to apply things such as perhaps stemming or lemmatization or removing stop words first of all, and then maybe also removing columns if their TF, IDF values are not very variable, they don't exhibit a lot of variation, that you might also drop those columns as well. Or you select still based on the frequency of each term, and libraries such as scikit-learn, also Spark, they typically make that easy for you. And if you would have been working with TF, IDF values in Spark, you do need to check the parameters of that pre-processing approach, because by default it's going to keep, or it's going to make these feature vectors very large. So if you're having issues with Spark is crashing because suddenly the matrix that I'm getting is exploding in size, well, this is probably why, because by default it keeps, or it makes a choice to keep a lot of these terms around, and you might want to reduce that. But we still get a feature vector for each document. And now actually already a feature vector that in most cases, if you're not like working with a corpus that encompasses the whole internet, but in most reasonably sized data sets, it's actually not too bad of a feature vector representation that you can make for documents. That's why it's still very commonly utilized. Here you see one example. So what was done here is you take 15 jazz musicians, you take the text from their Wikipedia page, you then apply a bit of stemming and stop word removal, so your vocabulary is 2000 tokens large, and then you just make for each of these documents, you extract that TF-IDF-based vector, which is then a vector of 2000 elements. And then you have a new search query, let's say, and the search query is famous jazz saxophonist born in Kansas who played bebop and Latin, and you do the same thing there. You convert that sentence into a TF-IDF representation using the same terms, of course, as the terms that are part of these 2000 that you had to construct your TF-IDF vectors for these 15 documents. So then you have 15 TF-IDF vectors, and you have also 2000 length TF-IDF vector for the search query. Well, then you can calculate some measure of distance between these two vectors, and typically cosine distance is used for that because we're working in high dimensional space, so that's a bit more common, the angle between the two vectors. And then you can rank the documents that you have based on similarity to the search query, and then you can say, well, the one that you're probably looking for is perhaps Charlie Parker, because that one gets the highest similarity score to the TF-IDF vector that you have entered me, or that you have given me. So this is still also for information retrieval questions. So this is what information retrieval is about. You have a certain search query, and you need to give me a ranking of documents that match best with your search query. It's still relatively common. Today, we will typically use models such as sentence embedders or BERT-based embedders using a Python package such as SBERT or sentence embeddings or an API key from OpenAI, which basically do the same thing. We give it a piece of text, and they give us back in some kind of black box nature a good feature vector representation for that text. We then typically do very similar things with these feature vectors, is we use something like cosine distance, and giving a text or a corpus of vectors, we try to match the best matching pieces. Very often, this is still done as kind of a step before you then work with an LLM, because maybe you have a corpus of documents from your help system internally, and your user asks a query. The LLM that you're using has no idea how your software works, so you want to give it a little bit of additional context in the prompt that you give it. Yeah, but which context? You have 10,000 help pages. Which one do you need to extract text from to stick in that prompt? You take the query of the user, you get a vector out of there, you compare it with all the vectors for these 10,000 pages that you have. You take the top 5 and you say, dear LLM, here comes a question from the user. And by the way, I'm copy-pasting also 5 pieces of text that will probably have or will probably contain the answer to the question that the user has asked. So utilize them if you can. This is called retrieval augmented generation, or RAG. Still very commonly done. It's kind of what consultant companies are making their bread and butter from nowadays, by building internal chat bots that you can ask questions to about your documentation or your piece of software. It's disappearing because as the length of input that we can give an LLM is increasing, we could also at some point just decide to take all the 10,000 help pages that we have and just dump all of them in the prompt directly and let the thing figure it out. There are alternatives to TF-IDF, especially in the space of information retrieval. This is also a pretty interesting one. This is called Okapi BM25, and there are other variations like BM10 or BM15, and the variations differ in the way how the values for K1 and B are chosen, which are the two user-choosable hyperparameters in this formula that you have here. Originally, it is meant not for a term and a document, but it is meant for a question and a document, to kind of see, well, how well does this document match with this query that the user has asked. And the way how it's calculated is you iterate over all of the terms that are in this question queue, and you multiply the IDF value of that question with this formula that you see here on the right hand. Details are not so important because libraries implement this formula, so by no means try to memorize this, but it's an alternative to TF-IDF. You might say, well, alternative, TF-IDF works on like the term level. Here you start from a complete question. Yeah, but again, you could say that every query that you give this thing is just one particular term, And so theoretically, you could just calculate again a BM25 score for each term and document, and then you can, instead of making a TF-IDF vector here, you can make a BM25-based vector for each term and document combination. And that would give you slightly different scores than what TF-IDF would give you, and in many cases also tends to work a little bit better than what these TF-IDF scores give you. In some cases has even been found to still work better than what you get out of embedding models, or in many cases they're combined. And Microsoft has an article where they show this off, how they did that, and also in the space of this retrieval augmented generation. So remember, in any case, what we utilize here, we still are stuck with high dimensional vectors, so we would have to apply feature selection tricks. 2000 is quite okay, but don't make it like 20,000 length vectors, and no predictive model is going to do well on that. You could also first decide to maybe apply something like the hashing trick from the pre-processing session to first reduce the number of tokens that you have. Or you could start with a vector which is indeed something which is 20,000 length long and contains TF-IDF scores, and then before you give that to your predictive model, you run t-SNE on top of it, or perhaps even better, you run UMAP on top of it to reduce the dimensionality of those vectors that you have. Or perhaps even something like a PCA in many cases would also work not too bad. So again, all the dimensionality reduction aspects come back into play. Now, the one thing that we haven't solved yet, and which is not easy to solve if you just try to stick to traditional approaches, is now every term gets its own score based on presence in the document and based on presence in the corpus. Fine, you get a feature vector out of there, but you do still lose a lot of kind of details of where this term was in that document. Terms follow one another, and in all the previous techniques, you threw away all this kind of sequential information that you have there. Yeah, you can have the token not, but if it follows with the token happy, well, then it basically says not happy, right? And again, you could try to apply small pre-processing tricks where you say, well, if I see two tokens not and then happy, I'm going to make like a third token out of there because I need to consider this as its own thing, which is different than just the word not followed by something else or happy followed by something else. So again, you could try to work on the vocabulary level. At the extreme case, what you could say is, okay, I'm going to consider every sequential pair that I have observed in my corpus. Instead of considering every word as a single token, I'm just going to make tokens out of pairs of words instead. And then you get a feature column. Every term then basically indicates a pair of tokens. Biggest drawback, obviously, is that you square the number of, or you, in the worst case, you square the number of features that you get, because now you're not just considering every word individually, you're considering every possible pair of word as its own token. So this will very rapidly explode. And you can decide to stick both what's called 2 grams or bigrams in there in this way, and then combine them with the 1 grams, but again, you're making the feature set larger. 3 grams, yeah, and in not a lot of cases would you dare to go to that level, because again, you're exponentially going to increase the set of terms that you will, or tokens that you will end up with. Now, at some point, and those are still available, Google has published data sets with frequency counts for 2 grams, 3 grams, 4 grams, based on this whole collection of books. If anyone still remembers Google Books, it's not getting a lot of love lately, but based on that collection of books that they have scanned and digitized, they have published basically publicly available data sets containing counts for every bigram, 3 gram in the English language. And before LLMs entered the stage, people utilized simple Markov-based models based on these counts to do text generation. If you have a text starting with I am, well, then you look at all the 3 grams and you do some sampling based on the frequency counts that you get there, and you kind of can see that, well, I am a potential completion for this sentence could be happy or unhappy or poor or rich, and you sample from there, and then you take the last 3 words again, and or the last 2 words again, and you try to complete the third one again, and you basically run like a Markovian chain based on that sequence that you have. You will not get Shakespeare by doing it that way, right? So these older Markovian approaches, they generate text which from far away looks credible, but content-wise are not very convincing, obviously. But you could play around with like setups such as those. Yeah, the next step then is, okay, you try to take machine learning and statistical approaches a bit further. And again, I'm not going to go into a lot of detail because today all of this field has been basically replaced with deep learning models. But basically, originally, this field tried to bring contextual information and negations and aspects such as sarcasm into kind of the use cases that were developed, and the use cases then typically being either part of speech tagging or named entity extraction or recognition, and things such as topic modeling. Right? So nowadays, mostly replaced with deep learning-based approaches as well. So part of speech tagging basically means that you try to give it a sentence such as this, and you try to figure out which are the verbs and which are the pronouns and the nouns and the adjectives and so on, maybe to utilize it as additional feature information, or maybe get a better understanding as a starting point to then basically figuring out, but there is a negation here, so it's not happy, but actually they are unhappy and things like that. These are early named entity recognition approaches where you give it a piece of text and you want to basically extract all the names of people, and you want to get dates, and you want to get organizations and numeric values and so on. All of this today is also typically LLM driven instead. So these are examples from both the Google API and from Spacie on the left-hand side. And then topic modeling, they're kind of early approaches that are very much statistical driven, also by looking at frequency of words as they appear over the different documents. So for topic modeling, both LDA and LSA were common early approaches as well. What is topic modeling? Basically, when people say topic modeling, what they basically mean is, well, what is a topic? A topic is a distribution over words. And you can ask the technique, or in most cases, you can ask a technique such as LSA or LDA, I want to get K topics. So in that sense, it's a little bit like clustering, you could say. You decide the number of topics that you want to get. And then based on frequency counts, again, basically the technique tries to extract, okay, topic 1 is represented by this word and this word and this word and this word and this word, and all of the words get a certain weight in there. And then if you have a new document that you want to see, okay, which topics are present in this document, you basically go check for each topic and for each word that's in that topic, is that word present in the document? We give it a weight. We sum all of that. Very often it's just a linear combination of products of these weights and their presence. And then you can say, well, topic 1 is 0.97 present in this document, and topic 2 is also 0.85 present in this document, and the others are not. It's still up to you, in many cases, to then give a good human-sounding name to those 10 topics that you have extracted, because the technique will just say, well, topic 1 is the presence of the word politics, and the presence of the word governance, and the presence of the word Congress, and the presence of the word president. Well, then you can basically go, well, topic 1 is probably about politics. Let's just call it that, right? So it will not give like a salient name on the topics that it extracts. That's still up to you. But then what you can do, if you have a new document, and in that sense, sometimes these topic modeling approaches are also utilized as featureization approaches, so you can utilize them for that. If you have a new document and you have 10 topics, and then you basically can get a vector that tells you, well, this document is 80% topic 1, and 10% topic 2, and 10% topic 3, and so on. Well, then those are your 10 numerical values, and maybe are a good representation, again, now linked on the topics that are present in the document that you then can give to a downstream classification model or regression model if you would want to. Also important to watch out for if you'd ever want to utilize a technique such as this with more traditional approaches is that if you would have very short texts, like tweets, for instance, or posts on or comments on social media, that especially LSA and LDA, they don't do very well. And then you have other approaches such as bi-term topic modeling or bi-term topic models that are typically better. So if you ever want to do something with this, then remember this, and yeah, why am I getting bad results with these standard statistical approaches? Because probably my texts are too short to extract meaningful distributions of words out of them. Some of them can also have topics that overlap with one another, some do not, so you also have a little bit of differences amongst there. And you have, of course, newer embedding-based approaches or completely, again, LLM-based approaches. Now, more important for us, to bring us to kind of back to the world of deep learning, is to take a bit of a closer look to representational learning, which is what we have been trying to do so far. In essence, everything that we have discussed so far is, okay, we get a feature vector for each of the documents that we have in our corpus. A more general question is, okay, but all of these approaches were kind of like manually driven in a sense. Like, okay, we calculate frequencies and we come up with a good score for them using TF-IDF or whatever, and then we decide how many of these stop words that we want to drop, or maybe infrequent words that we want to drop, and then, yeah, we hope in some way that these are good representations that we can do whatever downstream task, similarity matching or clustering or a prediction type of task on them. Okay, still, either we get very sparse representations, and that was also a problem that we had with dummy encodings for tabular data as well. There we also saw that one hot encoding, a categorical feature which has a lot of levels, is also something which is very sparse and probably not a very good representation. And if it's not too sparse, like something like TF-IDF does already do a little bit better there, it's still in many cases extremely high dimensional. So I'm looking for something that can maybe help me to reduce the dimensionality a little bit further. Not too small, but still a bit less than, let's say, 2,000 dimensions, and where I can utilize then the dimensions that I do have. I mean, even 256 dimensions, you can do pretty much with that, that I try to utilize this dimensional space or this embedding space as optimally as possible. And preferably, you might also say, well, I don't want to do that using some sort of manual formula. It would be nice if I can have this completely end-to-end downstream in a single model learned from the data directly. Why can't I have something that learns, again, good embeddings or good representations, similar as what TSNE did for us in the dimensionality reduction part? Why isn't there something that can do that directly from the data? Also, a bit more annoying is that yeah, I might have a representation for each word, let's say, and that is where we will start from. Then we will still have to figure out what if I then have a sequence of words, what then makes for a good representation of that whole sequence. But we leave that on the side for a little bit. So let's focus first on, isn't there something that can give me good representations of a little bit less or lower dimensionality, of good dense continuous values that I can perhaps utilize for whatever, or that are meaningful or worthwhile to utilize for whatever downstream task that I have. Maybe at a very basic level, I might want to say, okay, starting from the question of let's do this on the word level, if I'm going to embed or place each word in an n-dimensional space, I would like to be able to reason in some way with these vectors. I would like to be able to look at the vector that the word happy is placed, and then if I look around in the dimensional space, I want to find other words that indicate some positive emotion, right? And I would like to maybe do some vector algebra, and I would like to say, well, king is to queen as man is to, and if I go look there in the dimensional space, woman, for instance. So it would be nice if these vectors capture similarity, capture some relations between these words. And that's why I do still need sufficient dimensions. I mean, with 2 dimensions, you're not going to be able to express all of these distances. So I need sufficient of them so that I can capture different sorts of meanings between words and reason with them. That would be nice, right? And that's exactly what word embeddings and what word embedding models will offer us. We're working on the word level, which for practical cases is not so beneficial. Very often we'll work with complete sentences or complete documents, but these early models, they first proposed models such as these or embeddings such as these on the level of individual words. So we forget about documents for a second. We're going to say, okay, let's start with words, and my goal is to find a representation for each word, or again, token, if you would like to split it up on the sub-word level, but let's say for each word that I have in my corpus here. So I scrape a whole bunch of English books. I probably have all the words that appear in the English language. So for every word, I would like to automatically now come up with something that is a meaningful representational vector. Meaningful meaning then that I could use distance metric to define notions of relatedness between the items in this space, like or cosine distance metric again. But again, what really is a good embedding depends a little bit on the downstream task. We will see here in a second that the embeddings that we learned for our words, they do so based on a self-supervised mechanism. But depending on what your task is, you might end up with, or you might choose to construct embeddings or representations for your words that are better for the downstream task that you have at hand. Like we already saw this in the dimensionality reduction part. Yeah, there we were completely unsupervised. We just said, well, you start with a whole bunch of dimensions. You need to convert them to less dimensions. So again, you're going to embed something which is already a real valued vector, but you're going to embed it in a lower dimensional space. What makes for a good embedding there? Well, if you're PCA, then we said, well, things that are far away from each other should remain far away from each other in your new dimensional space. In the case of t-SNE or UMAP, we said, well, things that are close to one another in your original space, they should continue to be close to one another in your new space. Well, here, for these word embeddings, as a starting point at least, we're going to say, well, words should organize themselves in this embedding space so that I can do at least notions of relatedness and things like that, or comparisons between them. So in other words, these vectors should allow me to answer questions such as man is to woman as king is to blank. And good is to best as smart is to blank. And if I subtract man from king and then I add woman, then I expect that I end up somewhere in the region of queen, for instance. Here this is showed in 3 dimensions, right? Here it's showed in 2 dimensions. So this is not done on the original embedding space because that's typically way larger than 2 or 3 dimensions. But again, to visualize it, we then typically apply another post hoc dimensionality reduction step so that we can show things like these. Typically, for the original embeddings of our words, we pick something which is a bit larger, 32, 64, 128, 512 dimensions large. But what we do see is that even in these original dimensional spaces, that these embeddings indeed allow us to perform these similarity and analogy tasks. So, okay, that is already a reasonable starting point to have like a set of embeddings or a set of vectors for each words. And we want to learn them from representative text, so we're going to come up with a self-supervision task. We don't have labels in this case, we just have a whole bunch of text that we have gathered, and we want to get embeddings for each of these words. What we could do is there are different ways that we could take to do so, using things such as singular value decomposition or matrix factorization based, which are rather simple, but we're going to start immediately by having a neural network learn it for us, in a sense which is actually very similar to singular value decomposition, but using a neural network-oriented setup. What is a self-supervision task? Well, again, we could come up with different approaches. We could say, for instance, well, given a randomly chosen trigram that we take from somewhere in our corpus, so we pick 3 words from a sentence, try to predict what is word number 4 going to be. That would be a self-supervision task. In the models that we will introduce here, mainly Word2Vec, the self-supervision task that was chosen is giving a set of context words, so a 5-gram, for instance, that you randomly take out from your corpus, try to predict, you hide the word in the middle, and you try to predict the word in the middle. So basically, I take a sentence, I take out the word in the middle, and I give you the sentence with the word taken out, and I ask you, well, now try to predict what's the most likely word that should show up there in the middle of this sentence. Okay, how does that work? The end idea is then that we will also be able to utilize these vectors for other tasks as well. But let's first take a look at how Word2Vec works. It's already a very old technique, 2013. So we are at the early stages of neural network-based approaches for text mining, let's say, or for representation learning. So by default, it works at a term level, so for words, not at the whole document level yet. So we get a vector for each word. And we hope that it comes to represent then in some way, like we said, a meaning of a word in that embedding space so that we can capture relationships between words in an expressive manner. For the self-supervision task, as said, the central idea that Word2Vec makes is that a word that I would take, like my focus word learning here in yellow on this example, that this word is probably defined by the context around it, and hence is correlated with the context around it. So to set up a task, again, my self-supervision task is given a context, so something that comes before and after my focus word, and it will be up to us how many words I want to give before and how many words I want to give after, right? So that's something that you can pick, either the single word before or the single word before and after, or 2 words before and after. But let's say here it's 4, right? I take the 4 words, a window of 4, before and after my focus word. Well, then I can basically think of 2 self-supervision tasks that I can set up with this. And hence why we also have 2 versions of Word2Vec called CBO and skipgram. CBO, continuous bag of words, or continuous skipgram. And the 2 versions will boil down to, maybe the most straightforward one is, I give my model as an input the context, the green part, and I ask it, well, please predict me the yellow focus word. That's one way. The other way would be is that I just give you the yellow focus word, And I ask you, well, now try to predict the context from there. Both approaches are possible. Let's start with the simplest one, which is called CBOW. And CBOW, we give the context words as the input, and we're going to ask to try to predict the output word. Okay, in terms of encoding, both on the input side and on the output side, we need to start from some representation. I mean, we can't just directly shove in the word itself into our neural network. So we're going to pick the simplest, sparse, bad representation that we know, but then later we'll extract the better representation from the network. So for the context, here you see we have 4 inputs, right? 4 vectors, so that's basically a matrix with size 4 by v. V being my vocabulary, the length of my vocabulary. And we're going to utilize one hot encoding here. So if I would only have one context word, then my input is a single vector filled up with zeros, except with a 1 corresponding with what that context word is. If my context is larger, well, then we basically just add columns to this thing. Size v times the length of the context that you want to use, or v times c, whatever. We're going to connect this to a next layer. Connect how? Well, we're just going to use a standard or almost standard MLP-based setup. So the next layer, here we can pick the number of neurons that we want. So this has size n neurons. And this will govern the size of the dimensions that I want to end up with, or the size of the vectors that I want to end up with for all of the words that I have there. So there will be a first weight matrix that we need to train over here, W1. And then I have an output layer, so it's just a standard 3-layered setup. And the output layer, again, it's one vector with length v. So there will be a second weight matrix that I need to learn here. And again, here, basically, the thing is going to be softmaxed, because I'm going to predict probabilities. So I utilize a softmax activation here. So these will be probabilities, will sum to 1. And I will compare this with my true output vector, which is also one hot encoded, because I know what the focus word is. It was learning, if you remember, the yellow one. And I will calculate some loss between them and utilize for my backpropagation. So that's the basic setup of CBOW. Okay. With one context word, this case is still easy, right? And my input layer is just x1 to xv. My hidden layer has a length of n. So in this case, my weight matrix that I need is just v times m. And you do standard matrix multiplication. You multiply this weight matrix with your one hot encoded input layer. You get a vector with length n. And then you have your second weight matrix. This thing needs to be n times v, because we multiply this thing to this. We apply softmax, which is a bit hidden here, but we also apply softmax, and we get our output layer again of length v. So our input is v units. We have a w v times n matrix of weights, and we also have a w prime matrix of n times v. In this case, our hidden layer does not have any activation function. It's just a result of a straight matrix multiplication in this case. My output layer has a softmax activation function. Once this thing is trained, so I dump in lots of examples that I take from my huge corpus that I have, my context word only being a single word here. At the end, once this thing is trained, where can I get my representations from? Right? I'm not going to get them from the output anymore. Right? Basically, I throw away that part because that has length v. No, once this is being done training, I can either take my weight matrix W, right, which has, for every word in the vocabulary v, has a column of length n. That's the representation for that word. Or I could also take it from W prime, and then on the row level rather than on the column level, that would also be possible. You can choose. Most implementations will use the first weight matrix, but things such as GenSim allow you to choose as well. Becomes a little bit more tricky now once we increase the size of our context. So now my input is C times V in terms of dimensionality, because now I'm giving it a matrix. My hidden layer is still something which is n-dimensional. You might then think, well, if you just set up your standard fully connected weight matrix, then you would need C times V times N weights, because you're connecting all of the circles that you see here in the input layer to what's going to become your output layer. But you see here that instead, the weight matrix that we need to learn is just V times N. And the reason why this is done is because we're going to apply weight sharing. We're going to apply the same V times N weights here, multiplied by every column that we get from our input. So we apply the same weights, disrespective of where the word shows up in our context. That also means that this thing does not care about the order that the words are placed in the context. Right? Well, the reason why is, you might say, if we multiply this weight matrix of V times N with every column separately, then you get not 1, but in this case 4 outputs, all of them having length N. So initially you get something which is C times N, which is again a matrix. So if I would just multiply this thing column level, I would get not N, but I would get something which has, or which is a matrix of C times M. So in the case where you work with more than, so you get a C times N output vector in the hidden layer, we don't want a C times N output matrix rather in the hidden layer. We want something which is just N. Currently we have something which has still C columns over here. We're going to apply a very simple activation function step then on top of this, and we're going to say, well, just take the row-wise average over each column to collapse this thing down to a single n-dimensional vector. And now you see that it does not matter if we swap around the columns in this input. Yeah, we swap around the columns in this matrix that we generate here, but since we average them down anyway, they will become the same vector there. Right? So with word2vec, the order of context words does not matter. That gets averaged out. And then the rest is the same, because for the rest part, well, we have a single vector again. We again have this W prime that shows up here, right, which is still the same shape, n times v, because we need to convert an n-dimensional vector back to a v-dimensional vector, and we still use softmax there. So that's SIBO, basically. And then the idea is, if you just have enough data, then the vectors that you get in this W matrix, they will be good representations for the different words that you have. So here you can see an example. My input, it's rotated, so I have 3 context words, each of them being a one-hot encoded vector of length v. This is my weights matrix as it looks like currently, right? So my output will be C times N, will be the result of just taking this weights matrix and multiplying it in every row that I have there in my input. So I have 3 input rows. I get 3 output rows with a length of n in this case, because I decided that I want to have 4 equals m dimensions in there. Well, that's not the output that I want. I just want to have a single vector, so we just average the activations down on that level to average out the context dimension there. That also means that once this thing is trained, well, if I then want to get a representation for a single word again, I know that this is something which is one-hot encoded, so in that case, that's my single input. So every word, this is word number 1, 2, 3. Well, this simply corresponds to row number 3 in my weight matrix over there. So that's my representation. This 0, 0, 1, 1, that's my representation. Ah, yeah, but originally we picked a context C equal to 3, so if you really want to get the normalized representation, you can still decide to divide then every element in this weight matrix by C, and then you can just store this huge matrix that you have, and these are your representations for your different words. So at inference time, using this after training, this just boils down to a simple one-hot lookup in a weights matrix to get your representations for the different words in your vocabulary that you have. So using the weights of one of these 2 hidden layers is insufficient to get your word vectors after training. You can divide by the context size, but not necessary. You could just use the raw weights matrix directly. It's just rescaling it by a constant factor, so okay. The whole context and the desired focus is here represented as one training example, so you can make mini batches by just randomly sampling contexts and focus words from this large corpus that you have here. Remember that the ordering of the context does not matter, so there is still an independence of sequence in the inputs here. Sometimes, but don't believe this too much, but like folklore will tell you that SIBO is preferred if you don't have a lot of training data because the averaging activation functions allows for a slight smoothing effect. Whether this is really always true, I'm not so sure, and others are not so sure either, but at some point this is what people assumed, but not really well proven, to be honest. But okay, it's one of both techniques that you can utilize. Let's now swap it around. So skipgram, well, now the focus word is going to be my input, so that's a single word, again represented as a one hot encoded thing, vector. I'm going to again use one intermediate layer, and then my job is going to be to predict the context that appears there. And now the context will be an output matrix that I want to utilize, and again I use like a loss function to compare this with the true context that I have. We do need to be a little bit careful here now, because if we look at this example, or this architecture, let's say, the left-hand side now looks not too bad. We start with a single vector that again has v as its dimensionality, again something which is one hot encoded. And again we will train now a single weights matrix, v times n, and again we will matrix multiply this with the input to get some output, intermediate output activation vector, which has a dimensionality of n. Okay, so far so good. So now we have n numbers that we start from. What we do with these n numbers? Well, I need to have another layer that predicts the context from there. So now this thing magically says, well, I know that I want to get towards is a C times V matrix because my context has a size C, and each of the columns in that context, again, like I had here in the input side for the SIBO thing, each of the columns have like a length of V. And we stick something, or the parameters that we learned there is W prime, which is an n times V based thing. Same problem as before. If I multiply the matrix with size n times V with an n-dimensional input vector, I wouldn't get like something which looks like C times V. I would just get something which looks like a single vector with length V. Right? So if I start with something with a length of n, and I have W prime here, which is n times V, if I multiply this thing, I just get a singular vector V. The way how this is suggested here, on the picture at least, is, in this case, what you do is you also use weight sharing, so it's the same W prime that shows up there, and just multiply then multiple times with this output that you get from there to get your first context word, your second context word, your third context word, and so on. Yeah, but how? You're multiplying with the same thing, right? So that wouldn't really work in this setup. So the picture here, again, it summarizes a little bit what's going on here, but we do need to be a bit careful. What's happening here instead is that now the goal of this network is not going to be to immediately try to predict the whole context. Instead, the context words are presented as training examples, one by one. So one example is going to say, okay, focus word learning on the input. I expect you to predict now the first word in my context. That's what I will calculate the loss on. And the first word in my context is, I forgot what it was, a goal maybe. And then there is a second word in this context, which is, and so on. And now these are just separate training examples that I give to this network. So effectively, every time I'm always just asking to predict a single context word. And hence also why the order doesn't end up mattering of the context that I'm trying to learn here. Well, why? Because we're shuffling the mini batches that we give to this thing. You might say, well, isn't this a bit of a crazy task? Because for the same focus word, the first time you kind of asking the network, hey, try to predict goal. And if you can't do this, I'm going to calculate loss on this and update your weights. And now the second time, given the exact same input, I'm going to ask you to predict me the word is. But you just said it was goal. How can you expect me then to learn from this? Well, I really don't. The best thing that I know that you can do is probably update or show me a probability distribution over here where both the words goal and is and other words that show up in that context get a high probability, right? So I know you will never get it perfectly right, but you will get as close as possible, obviously, right? And the same actually for SIBO also there. With shorter contexts, you can have the same context, but I can ask you to give me a different prediction on the output side. And again, there, the best that you can do is distribute your probability mass across all the focal or the focus words that show up for the same context. And at the end, I even don't really care that much about your predictive capabilities or the loss that you end up with. Of course, I expect the loss over training to get better and better, because I only care about what's in these weight matrices at the end of training anyway. There is another way how you can set up SCG. So this is the way where you present these examples one by one. What I could also do is I could say something where I say, okay, on the input side, I have one vector with length v, which is the focus word, and I'm also going to give the context word on the input side as well. And then I utilize some weight matrix where effectively I need something which is 2 times v times n, because I want to end up with like something which has a dimensionality of m. And then here I can reduce this down to a single neuron with a sigmoid activation function. And now this is going to be a binary classification task where I basically have the thing guess, hey, does this context word show up for this focus word or not? Then I don't only need to take positive samples from my data set, and I also need to take negative samples from my data set. And I also need to give it examples where the context word is not a part of the context for a particular focus word. That's another approach how you could set this up as well. Now, in any case, the idea is that after we train a network, we throw it away and we just utilize one of these weight matrices where we extract our vectors from. And the size of the hidden layer hence determines the size of the size of the word vector dimensionality. It might remind you a little bit like how an autoencoder architecture worked, because also there we were trying to squeeze something high dimensional to something intermediate, which was lower dimensional, and we also said, well, now we just use the intermediate activations in that case as representations for our instances. Now, what do implementations then do a little bit better? Be a bit more clever with the random context word selection, maybe use subsampling so that you don't always retrain on frequent focus words, for instance, because the word this will probably show up a lot in your text, so maybe skip over that. Negative sampling means that you're a bit clever and realize that, well, since your output in this SIBO thing is something which is one hot encoded, the number of weights that you need to update here and that you need to update in this weight matrix is not a full weight matrix. It will only be like particular rows in that weight matrix, so you can also make your implementation a little bit efficient there. What do you do then? Visualizations such as these are similarity tasks. You make word vectors with a dimensionality of 1,000, so n is 1,000, and then you apply PCA or t-SNE if you want to make visualizations, or you run cosine similarity tasks on top of this. So those are typical cases that you can then utilize. Nice, works well. There are other techniques such as GloF, very similar to Word2Vec. A little bit better because it also exploits statistical information with regards to word co-occurrences and so on. And then there is also FastText of Facebook, which is also very similar, except that there they made the decision to say, hey, we're not going to learn a representation for each word specifically, because people tend to misspell words a lot on our website. So we're going to do it on the level of little character n-grams instead. And now we get a representation for every n-gram, and even if there is a word that we didn't see yet because you misspelled it, we can at least then get the representations for the character n-grams and then probably average those representations to get a final representation for what this word should be instead. This is still somewhat commonly utilized in industry cases as well. FastText became quite popular as a word embedding, or character n-gram rather, embedding model. Another reason why they did this, and this is one of the largest drawbacks of the way how this Word2Vec architecture is set up. It is a parametric model in the sense that it's fully end-to-end downstream learned. But if you think about how the architecture is set up, what if tomorrow you tell me, well done, you have obtained n-sized vectors for all of these words in your vocabulary, and you have 20,000 of them in there, but now there is a new word that for some reason you didn't have in your training corpus, right? Like a misspelled one, for instance. What's the vector for that word? You have no way because everything is one-hot encoded in the input side and in the output side, you have basically no way from this weight matrix to then say, yeah, but for this new thing, which was not part of the original vocabulary, which is not part of the original item set that I created embeddings for, so I have no way to give you a vector for that thing without retraining the complete model, but then all the representations that I got for the words that I already had might also change. So this is something which is not easy to apply at inference time on the level of, or when new words would appear. Now, luckily, vocabularies of languages are relatively stable. If your data set is large enough, then that wouldn't really bother you that much. Likewise, if you do expect misspellings, then you could decide, like Facebook did, to make a representation for subparts of a word, and then just get a representation for each piece, and then average them or concatenate them in some way, and use that as your final embedding. So, okay, all of this is fine, but very often, like I said, our instances that we work with, they are not words, rather they're going to be complete documents. So what I really would like to get is not a representation for words individually. I would like to get a feature vector representation for a complete document that I can then give to my downstream classifier or whatever. What are ways how I could set it up? Well, an early attempt was to do something sneakily, like was the case in Part2Vec or Doc2Vec. And the sneaky part said, well, in our vocabulary that we have, so this is SIBO again, in this vocabulary set V, we're not just going to take all of the all of the normal tokens, a, this, learning, and so on, so the set of all of your words, but then we're going to also take the documents themselves, which contain these words, and you have maybe 10 of them, and we're also going to slap in some dummy tokens, you could call them, which we just call doc1, doc2, doc3, and so on. And then we're going to set up the same SIBO approach, for instance, as we did previously. And we're not just going to give the surrounding words as the context, which in this case is the, cat, set. But the first context vector, or could be the last one, since order doesn't matter anyway, that one is going to represent, in this one hot encoded part, well, this is document number 2, so here we put a 1 in there. So this is basically context representing or telling me, hey, what's the document number that we're talking about in this context? So now your weight matrix, well, you have V times N in there, so your weight matrix will not just contain still representations for all of the words that you had in this vocabulary V, but at the end will also contain representations for this document 1, document 2, document 3 tokens. So we just code train document identification tokens as part of the context with normal word tokens as part of the context. And then you also have a vector for each of the documents in your corpus. But still, issue, because yes, that was my train set of documents. Now I would like to get the vector for a test document. Similarly, we can't just slap at inference time, make this vocabulary length longer and say, well, now it's this document. Your weight matrix is fixed, will not work that way. So that's it's still not going to be useful for inference tasks. So we need something else. Early approaches then said, okay, you know what, since you have a vector for each of the words, what is then the vector for a document? Take all of the vectors for the words and just sum them together, or just average them together. So those were early ideas, and then you have a document vector, just use that one, that works in inference as well, and then do something with that. Yeah, for smaller texts, reasonable, right? For longer texts, of course, you can't just expect that you take like vectors for each of the words and just average those together and expect to get like still a good representation for the complete document in there. Now, this approach of what's basically word embeddings has been applied on or towards solving the problem of high-level categorical features as well. And you can do that in exactly the same way by setting up an architecture that looks quite similar to this SIBO thing that we just looked at. So basically you say, okay, I start with a one-hot representation with length number of levels in my categorical. And I then connect this to a next layer where I want to reduce this to an n-sized representation. and then I connect this to a next layer, and probably I'm working in a binary classification task anyway, so this can be a single neuron, and I'm just going to ask it to predict the true label that I have here and apply my loss function. Well, likewise, at the end of the day, you have your weight matrix length L times N in here, where you can also get your reduced dimensional representation for all of the levels in your high-level categorical. So you just pre-train a neural network first, you take the weight matrix out of there, you store that somewhere, you throw away the rest of the neural network, and you have embeddings for all of the levels in your categorical with a length of your choosing, right? Similar as how weights of evidence encoding gave us a single, quite dense number, a scalar for each of the levels in our categoricals. Now you could basically say, well, I don't want a single number, I want something with length n, and also something that's been trained already with the supervised task in mind there as well. But again, only on the training data, you use the same weights to get representations on the test data. This has been done in early papers, 2016, 2015, get relatively good results. Of course, if you're planning to utilize a complete neural network for your whole task anyway, you wouldn't do this, but this can be nice where you say, well, I do want to use XGBoost, it's just for this high-level categorical that I need to fix it in some way that I can get like a good representation for each of the levels. So I'm first going to extract that from a neural network and then utilize this as a feature representation for that feature and its levels only. So here you can see some examples of what these embeddings look like. So here the downstream task was predicting sales of a supermarket, a very low dimensional size because there aren't a lot of number of days in the week. So it's not that this is a very high level categorical one, but it does show that the model basically places Thursday far away from Saturday, and probably because Saturday there were like a lot of weekend promotions going on, so people like to shop on Saturday. Maybe the least preferable day to go shopping is Thursday, and close to that is like Monday and Friday, and then Sunday and Tuesday are somewhere in the middle. So that's basically what these early attempts did with that. So if you want to generalize the concept of an embedding, it is simply you start with a set of items, a set of words, a set of high-level values from a categorical, a set of images, a set of whatever. You one-hot encode them, right? You stick a weight matrix on top of that, and then you fill in this weight matrix by training based on some downstream task, which in the case of Word2Vec was self-supervised, or in the case if you're doing binary classification anyways already, can be completely supervised. You throw away that neural network, or you then do something else on top of it in your architecture, but that weight matrix then basically contains the placings, the embeddings for each of the items that you have in your original set that you originally represented using one-hot, but then with a lookup in that weight matrix get compacted to a more dense representation. In Keras, this is a single layer, for instance, called the embedding layer. What do you learn? A weight matrix with size, length of the set that you start with, number of items that you have, times number of dimensions that you want. And then basically have the model fill in all the cells of that weight matrix as good as possible to minimize the loss. What's always the drawback if you want to use, or if you try to learn representations with this embedding-based approach, is that you always start with a set of items of a fixed length, number of words, number of levels, and so on. So if you like to apply this thing at inference time on new instances that become part of that set, then this approach on its own is insufficient to get good representational vectors, because your set has a fixed size, because your weight matrix has a fixed size. So if you say, well, I'm really working with documents, and at test time, at inference time, I will have new documents, and my network needs to come up on the fly with good representations for new cases as well, then we need a different approach, basically. And that's also what t-SNE suffered from, for instance, as well. A different approach where maybe we do not start with something that is one-hot encoded anymore, because it's this thing that kind of induces this fixed length, but where maybe we say, well, what's the other approach that we can take, is instead of saying, well, start with a set of items which is fixed, and just learn directly which values that we should give to each of these items. Well, if you want to have something which is more capable or more suitable to be utilized for also new items that might show up, well then very typically, and that's what you see all over the place, that's what we saw for images in a way already, but that's also what you will see for nodes in a graph next week, but also what we can do for text, is that we say in some way, well, what we then really need to do is not just start from this is item 1 and this is item 2 and this is item 3 and just directly learn a representation for that, but that we start by saying, okay, how can we get a basic description for this item per item based on some, still features that we extract from them. And then based on those features, we convert them down using an MLP stack or some other type of units that we have in our architecture to a representation. And then even if I have a new item that shows up, I can start with its basic feature description and then convert it down to a feature vector representation. But again, for text, what is a simple feature representation that I can come up with if I have a whole document? Well, I can still decide to keep it simple on the one hot level per word, because there I can kind of assume that I at least have a vocabulary of a fixed length. But now my documents have not a fixed length anymore, and also the content of my documents and the number of my documents is variable. So for every document that I have, I could say, well, a document is a matrix consisting of a sequence of words, which I then, again, one hot encode. So every column has length v in here. I could also say, well, let me first utilize word2vec at least to make this a bit smaller. So then every word in this sequence is its word2vec representation, right? Which are numbers between 0 and 1, so which are a little bit more dense, of length n. Problem will still be, yeah, but this is still the variable part, because some documents are shorter, some documents are longer. You're working with a sequence of things. Simple fix number 1, you just say, well, I will take an upper limit. And I will take the 90th quartile of my document lengths, and if my documents are shorter, just fill it up with zeros, and we do it that way. And if my documents are longer, we just cut them off on the right-hand side or the left-hand side or whatever, so that they fit in this matrix. And then basically you have a starting bunch of numbers that you can then connect to an MLP, and probably you will also apply like some form of weight sharing over the columns so that you can reduce down to a single feature vector representation again for a whole document. But now if we would say, okay, but I really want to have an architecture that's capable to deal with input sequences that are really variable in length. Isn't there something possible? Everything that we have seen so far, like for an MLP, it assumed a fixed set of inputs. For a convolutional neural network, there we already saw a fully convolutional setup where the images at least could be of different size. What about this thing? Could I also come up with something? You could maybe apply a one-dimensional convolution on this thing first, a couple of times, and then use global average pooling based on the number of levels that you get, and then you do get a fixed feature vector representation. So that would actually work. We could do a one-dimensional CNN without max pooling or without average pooling, but with global average pooling, and then it doesn't matter how lengthy that this thing is anymore. So that's actually already one way how we could tackle this. But again, if you get very long documents or very long sequences, basically every element in this sequence could even be a single number, if you're talking about time series, for instance. Yeah, we do know we can try to increase the receptive field of a CNN by stacking layers on top of each other, but at some point probably that will, or we could expect that this will break down. So if my sequences get even more lengthy, isn't there maybe another thing where I can set up an architecture that can handle this? Yes, and indeed there exists a unit like this, and this unit will be the recurrent neural network unit. We'll do this after the break. First, some further examples of what you can do with these embeddings. These are embeddings, and the words here are highlighted based on the sentiment. So this is not part of the embedding itself. This is just a coloring that was done afterwards. Also just goes to show that these words positioned themselves relatively well in this already 2D space that we have obtained from here. People have also utilized reasoning with embeddings to kind of reveal biases that are part in the text corpora that we utilize, and see how the meaning of a word changed by following it throughout time, right? If you take the word, the typical example that they utilized, if you take the word gay and you look at newspaper articles from the 1940s, then it used to mean fun and pleasant, and then it got like different meanings, both negative and positive and so on. How is that done? Well, again, by playing with the vocabulary. If you have a certain word, happy, and you want to see how it changes throughout time, well, then basically for every decade, for instance, you want to place that word at a different place in your embedding space, so you can just slap the decade of the original or of the text where that word was taken from together with the word, so that you have happy 40, happy the 50s, happy the 60s, and so on. And now just all of these tokens are different items in your item set, and they will get a different position in your embedding space, and then you can follow them, and then you can say, well, happy in the 40s was very close to words such as lucky and rich and so on, and now today it's closer to words such as travel and so on, right? And you can do things like that with those. Airbnb has played around with them to create, like, this is more on the tabular level, embeddings of listings, and I'm visualizing them or clusterizing on those representational vectors that you get, overlaying the colors of these clusters on a map, and you see that the embeddings that you extract from the features of an embedding are very heavily linked to their geospatial location underlyingly as well. News sources, you can take a bunch of articles coming from left-wing news sources and right-wing news sources, and then you can compare like where certain words end up in their embedding space. So this is from a more right-wing, Republican-oriented set of news sources, and then if you take a look at the words where Obama has been placed, you see that administration is closed, and Reagan is closed, and deplorable, hater, loser, unpresidential, those words are also closed. And of course, Obama would be placed differently in a left-wing bunch of articles. An interesting kind of look ahead to next week is that there also exists something which is called Node2Vec, and which is a relatively clever idea. And Node2Vec says, okay, let's say that you have a graph and you would like to have a representational vector for each of the nodes in your graph, because then you can cluster them again, or you can do whatever that you want with them. Can't we just apply Word2Vec as well? Yeah, but Word2Vec works on sentences, not on a graph. Yeah, but we can create sentences from a graph. How? Well, just start somewhere at random at some of these nodes in this graph and walk around randomly and just make sentences that keep track of the node identifiers. We start at node 10, and then we went to node 11, and then we went back to node 10, and then to node 8, and so on, until we decide to stop randomly. And we generate a whole bunch of these random walks. We dump that into Word2Vec. We get a representation for each of our tokens, but our tokens are nodes, and ta-da, you have a representation for each of the nodes in your network. And then you run k-means on those representations, and you color them based on the cluster that they fall into, and you see that these representations indeed indicate some sort of structure in the network. The purple ones are more at the outset and so on, or the ones with a lot of nodes being connected to them. And by maybe biasing the way how we walk through this random through this graph, we can also get different sorts of representations from there. Fun technique, was again pretty popular for a while. Same drawback, if you do it that way, tomorrow you have a new node that shows up in this graph. Maybe you're doing some sort of churn prediction or whatever, fraud prediction. Yeah, tomorrow a new node, what's the representation for that new node? I can't, right? I started with a fixed set of items, so again, if I need to do that, I will have to start not by saying, well, you have 100 nodes. No, the only thing I can start from is saying, you have a node with these are the features, this is its neighborhood, learn me a way to then extract a representational vector as part of the neural network architecture directly. And that's exactly what the graph neural network will do. That's also for next week. But you see here that the initial attempts were very similar as the things people used to do for text as well. Okay, our announcements next. First, let us go for a 10-minute break. Okay. Moving to the recurrent architecture. So remember, our issue is we have a sequence of text, and we're going to say, okay, every token is represented by its vector representation, either something which is one hot, or maybe already the result of something like a Word2Vec. But we have a sequence of elements, and the sequence is not of a fixed length. So how do we deal with that? Already seen, well, we can try to make it a fixed length by applying capping-based approaches or window-based approaches, or we could say, well, I'm only going to give to my model the last so many items that I have. Earlier approaches said, well, if you have a word2vec for each of the words, then just average all of them down to get like a single representation like this. I also just said, well, or not theoretically, you could also thinking about a one-dimensional CNN setup, where basically every layer of CNN units that you add creates K filters, and then on top of there, you do a fully average pooling layer to get your final vector. The recurrent unit is something that is another strategy that is capable to deal with sequences of a variable length. And they're called recurrent because this is a unit, a neuron, which will perform the same task for every element of a sequence, non-respective of how long that sequence then is. And the output will be dependent on the complete sequence and all the previous computations that happened over this complete sequence. In essence, it's not so difficult. What does an RNN unit do? Well, an RNN unit, I'm again going to represent it as like a circle for my neuron. At the basic level, what does this thing needs? It needs the input at the current time step t. So in the very first time step, that will just be this very first vector that I have, as well as the output that the model produced in the t-1 time step, which is typically called the hidden state, which is also a vector representation. At the very first time step, I don't have a hidden state yet. So in that case, well, h-1, or if t is 1, then h0 is some randomly initialized vector that I start from, or a vector with completely zeros. At every time step, it takes this current input at the current step and previous hidden state that it produced, and from there, it will compute a new, or it will output a new hidden state for the current time step. And then if I give it the next input, so then I move towards giving this word, I feed in this word in the input, but I also feed it back the hidden state that it produced in the previous time step. So this is not the same as just giving it the current word and the previous word. It's giving the current word or the current element in my sequence plus the previously computed hidden state update that it produced. Of course, for this thing to work well, it's going to have to keep around all of the meaning that it wants to keep inside of its memory, let's say, as being a part of that hidden state vector that it basically passes on from every time step to the next time step. If currently you have a feature vector which is representing as the input open parentheses, well, then somewhere in this hidden state representation, it will have to keep track of the fact, hey, careful, parentheses have just been opened. If the user is asking me what's going to be the next, let's say, word or token that appears here, probably now I need to remember somehow that close parentheses has become more likely to be obtained. Speaking of making predictions, how do we utilize this thing to then make predictions? Well, typically we take this hidden state thing that it produces, and we also put an additional couple of layers on top of this, which could be MLP layers or whatever, and then we again go towards the output that we want to obtain, which perhaps is again a soft-maxed output with a one-hot encoded kind of output that we expect to compare this thing with, because maybe I'm predicting the next word in the sequence. So then if I have an input sequence, maybe one-hot encoded or maybe word2vec encoded, but already encoded in some way based on the element level. This could also be a sequence of, if you have time series data, then this is just basically a series of numbers, 2, 3, 5, 7, and so on. I go every time step, I take the input at the current time step, plus the hidden state that you gave me at the last time step. For every intermediate time step, let's say that I'm here, right? I give you 5 as the input plus the hidden state vector that you produced me in the last time step. I could basically then tell you, now update your hidden state, and based on your hidden state update, you should be able to predict me that the next number in the sequence is going to be 7. Right? And I can again calculate the loss based on this and hopefully improve the inner working of this RNN unit. So during training, I go through this sequence time step by time step, and probably already at every point in this time step, I can compare your output with some desired output that I want to see. If I'm doing some sort of time series analysis, then that's probably what I would go for. What I could also decide to do is basically don't do any weight updates until I've given you the full input sequence, and it's then that I want to have you produce based on this final state vector that you have then obtained, that from this point I want you to produce an output of a certain shape. For instance, what's now the next word in this sequence, for instance? Or what are the next 3 numbers in this particular time series that I have here? Then again, I have some laws that I can calculate, and I can perform weights update, even though we don't really know how these weights exactly look like, but I can perform a weight update that way as well. So very often, we just utilize the last hidden state, which is produced as a final time step, and I calculate, or I produce my desired output from there, and I calculate my loss. But I run recurrently through my input sequence. So now here, the ordering that I give you these items in does start to matter, because it's only after time step 0, 1, 2, 3, you always perform a next update of your hidden state, of your internal memory, so to speak. So now I can also take the order into account, and input sequences can be arbitrarily long. There's one thing which is a little bit more tricky, and we need to solve that a little bit later. But then what on the output side? Here I have said, well, I either predict a single number, or I predicted the next word in the sequence, or I predicted the next 3 numbers in a sequence. What if I also want the output to potentially be of variable length? If you think about translation tasks, I give you an input sequence in one language. The output that I'm going to produce from that I want you to generate from that in another language, I don't know what the length is going to be. Right? I can set a maximum cap on this, for instance, and then hope that it matches again in that window. But maybe also on the output side, I would like to have something that can generate me variable length output sequences as well. So far, we don't have that yet. We'll come to that a second from now. But here we can already deal with it on the input side. So this is basically what we are doing. We have inputs at every time step, and our network hence now has a certain state that it reaches at all of these time steps, represented by this hidden state vector that it updates depending on inputs at time t-1 and the state at time t-2. So now the order in which we feed the input elements to this network will of course be important. Now, what does it look like internally? Basically, it's like you have some sort of a for loop that you have built now. The for loop saying, well, for every item in the sequence, give this item to the network together with its last output and get the new output. And then you go to the next item, the next item, the next item. So very often, it's drawn with like a loop, as you see here. Becomes a bit tricky to perform backpropagation, because to do backpropagation you need to basically pass that backwards through the sequence that you've given it. That's called backpropagation through time. So you need to unfold basically your neural network like this, where at every step you have an input sequence and you have a hidden state that gets produced, and this hidden state also gets passed as an input for the next time step as well. So a little bit more tricky to set up in terms of having to do that manually, but typically you don't have to code that manually, so okay. Again, this is not just the same as making an MLP where we give the current input and the last input, right? We give the current input and the last produced output by the network. So the network now becomes free to choose what to put in this state vector, this output vector, to kind of learn how to keep track of everything it has seen so far, and to hopefully at least remember what to keep and also decide what to discard. So in theory, they can work with arbitrarily long sequences. You could say, well, if we make this hidden state vector of a very high dimensionality, right, then this is something that could work with an arbitrarily long sequence. In theory, because in practice they still tend to forget things and are only limited at looking a few steps backwards. That's also why we have different instantiations of these RNN units. But at least theoretically, they're like, they offer some nice promises there. Yeah, and if you now think about how can I produce a representational vector for texts which have an arbitrarily long length, well, this hidden state vector that you obtain after having fed all of the words to this RNN thing, right, that might be a representation that you could utilize. How do you then, what's your supervised task? Well, given the words that you have seen so far, please predict me the next word in the sequence. And then I expect that if I give you a new sequence and you give me that hidden state vector that originally I would have used to predict the next word in a sequence, then maybe that hidden state vector is also a good representation for the document you have seen so far as a whole for the input that I gave you, which is now that sequence. So, okay, interesting. A for loop in a network, but training it is also hard because we get all these problems of vanishing gradients because we are now backrolling through time, which are even more pronounced. The initial state that we give, yeah, all zeros or something randomized, but this can also be quite severe. So I can just easily say, well, the first hidden state that we give is something random, but in practice this can also turn to be a bit more cumbersome. And also because this is a thing with a self-feedback loop, yeah, if it starts blowing up values in this hidden state vector that it produces, the next time you're going to give that same output again as part of the input, yeah, you can run into bifurcations or things that blow up very rapidly and make the whole system unstable. So also this makes training these things in practice is not so easy, and you need to apply things such as gradient clipping and stuff like that. But luckily, that's what many of the libraries make easy for us. Maybe more interesting is to take a look at, okay, what's inside now of this green box A that we have driven or that I've drawn, or what's inside of this circle that I've drawn here on the blackboard. Here, you see that at every time step, except for the first one, but actually also there, it's a pity that they didn't draw it, but at every time step, it receives two things: the current input, so here this is xt, and the hidden state that was produced by the previous time step. So let's hear what comes in on the side, and it takes in the current input. So the current input is maybe my word to vector for the current word that I'm giving it. This is the hidden state that it produced last time. It's going to do some internal stuff, probably with a bunch of parameters that it's learning, because that's the whole idea of setting it up as a neural network, that there are some parameters that we'll have to learn. And it will utilize these parameters to produce a new version, an updated version of this hidden state at this time step. And either we can use, and this is why it gets split up, typically we then utilize this hidden state to connect this further to like an MLP to then do predictions with, but also this hidden state gets passed in as part of an input for the next time step that we give it. You already see here that there is this tiny box here saying 10H, so there is something with a 10H that happens here, and merging lines and splitting lines, whether this is a sum or a concatenation or a product, hard to say if you visualize it this way, so maybe this makes it a little bit clearer. This is basically the formula that you get for the most simplistic version of an RNN unit. Okay, at every time step we have a vector representing our current word or a current thing in our sequence that we're looking at. We're multiplying this with some weight vector or weight matrix again that we get here. So we multiply WAX with this X vector that we get in. Similarly here, we also receive the last hidden state from the previous time step. Also this gets changed by multiplying it with some weight matrix AA that we have here. We then sum these things together, plus we add some bias to it to obtain like our final summed vector of these two updated things. We then run this through 10H so that we get clean values between -1 and 1, and it's this thing that will be utilized as the updated hidden state. Yeah, if you then want to do something else with this hidden state, like put a softmax on top of it because you are making predictions of some sort, you can also do that here. So this is free. You're free to do also with this hidden state what you want to do downstream. So softmax then on your input makes perhaps a bit more sense. There are other instantiations like LSTM, and stands for long short-term memory, and also GRUs, which make this internal box a little bit more complicated. It was found, like I already said, that with this simplistic RNN approach, yeah, everything that you're trying to do here is in the form of these two weight matrices, right? It's this thing that basically massages your input vector to get like the right number of values, and it's this thing that takes in your previous hidden state vector to become something updated, and then you add it together, and then you add some bias to it. But you can also see that like the link between what we do here on the previous hidden state vector and what we do on the input of the current time step that we receive, it's quite independent of each other, right? Preferably, you would basically want to get something that is capable to say, well, the way how I should work with this hidden state vector is probably not just by always multiplying it with this fixed thing over here or with these weights, but probably will also depend somewhat on what this input looks like. And the only way how I can do that here is because I know that I'm summing them at the end, but it's maybe not the best operation to utilize there. So LSTM makes this a little bit more complicated by adding in things such as these and then more mixing terms and saying, well, first we're going to take this input and we're going to apply a softmax on this, and then we can multiply this with, we don't use one hidden state here. We in fact have two hidden states that it utilizes. Both, this is then typically called a hidden state, and this is called the cell state. The hidden state is a thing that you connect with your downstream task, but both of them also get passed forward to every next time step. This is a thing, again, internals not so important, but which is deemed to be, and actually it's a very old technique, but which is a bit more capable to update these two hidden state vectors in such a way, and that's what these different operations want to do, is depending on the input that I'm currently receiving from you, what are the parts that I should forget from these hidden states that I have here? And the basic way how this is done is if you put a softmax somewhere in the middle, you have things that become very close to zero. If you then multiply that with your hidden state vector, as is done here at the top, then you're basically just wiping them out from your hidden states. Every time you see like a multiplication and there is a softmax before it, attention mechanisms will also do this. It's basically saying, well, this is not important anymore, multiply to something close to zero, and other things that you might want to retain for a bit longer or might want to give a higher importance there. So a bit more complicated internals works a bit better for long sequences. This is quite similar, a little bit in between, a little bit more simplistic. They train faster. Very often, if you have less training data, tend to do a bit better than LSTMs. Practice varies. Whether LSTM or a GRU unit works best up to what the data is that you're working with, so you might want to try both. That's the basic idea. You can then think about ways that you combine CNN models with RNN models, where you, at every time step, you first run a segmentation model, and then you have a sequence of images. Then you're reasoning about video, right? And then I give you a sequence of images, and that can be arbitrarily long, and I want you to tell me where I should move the robot arm towards. So also, this is already kind of at the edge of easy to set up on just a single machine on your own, but the architectures are still relatively understandable in the sense that, okay, this is a combination of this recurrent thing and this convolutional thing there. Also very common is to go for a bidirectional approach where you basically have two versions of your RNN network. One where you go over the input sequence from left to right, and one where you go from right to left. This is not the same as cheating and looking at the future. In both cases, in the first case, you're telling, okay, I give you word number 1, word number 2, word number 3, word number 4. Predict me word number 5 now. For the other RNN, I'm giving word number 4 first, then 3, then 2, then 1, and then I'm asking, predict me word number 5. The reason why this is done is, again, to help a little bit with these input sequences that are a bit longer. Because by the time you come to the end of your input sequence, that hidden state vector probably has already forgotten a lot about the things that it saw at the beginning of that sequence. Well, then let's swap it around and let's give it in this way as well. This is called a bidirectional RNN. But it's more like a fix to deal better with these longer input sequences. And then we can also say, okay, let us try to then look at a translation-based model where now not only the input can be of variable length, but also the output is something that needs to be of variable length. And now we come also a bit more towards generative use cases. I mean, here we kind of have like a use case where you're translating from one sentence to another sentence, but you could use exactly the same setup to say, I give you part of a prompt, a beginning piece of a story, and now you complete the story for me, for instance. So you could also think about generative text models by using a sequence-to-sequence model style thing like this. How does it work? Well, it uses an LSTM here, so we do need to take into account that at every time step, there are two hidden states, H and C, that are passed on as an input for the next time step. The input part, or the encoder, is relatively simple. We already kind of know how this works. This just goes through the input sequence at every time step. I give you the word I and just an initial hidden state. You produce me an update for H and C. Next time step, I give you like as the input, one hot encoded or whatever, and your previous hidden states. You give me an update of your hidden states. And I give you the last word, cats, and you produce your final hidden states. Then I have a separate RNN stack. And that RNN stack in the first time step contains a special token basically saying, please start generating. There is nothing yet, but I do need to give you something. So this is maybe a special token in my vocabulary, or it's all zeros or whatever. But I'm basically saying, well, start your generation. That's your first input, is to start. You receive the hidden state and the cell state, or simply put, the hidden state, which was last produced by the encoder. That's the one that you receive now as your initial hidden state. You produce an update for H and C, but I'm also going to grab H here, and I'm going to put a softmax on top of this and convert this back into a one-hot encoded vector to kind of know, okay, what's the word that you predicted for this time step? Jam. Next time step, I'm going to take now not just your previously updated hidden state to give as an input, but also your last produced output I'm going to sweep back in as an input for you now. So this is basically autoregressive generation. Now this decoder thing is starting from like a fake or like a dummy start generating token, as well as the hidden state produced by the encoder. And from there, it just runs ahead and it predicts upon itself. This can go forever. When does it stop? Well, just like I have a start of sequence token in there, I also have a special end of sequence token. And from the moment this model says, well, now the token with the highest prediction is end of sequence, well, then I stop asking you to generate further. Right? I could ask you to generate further, in fact, but I don't do that because also in training, I stop them there. I told you, well, after now here, I expect you to predict something that gives me gem, and I can update your weights based on this, and then la, and then la sha, and then the next thing should be end of sequence. So this is a model that gets trained completely downstream based on this task in terms of what it needs to predict. This has a drawback, and a drawback here is that if you look at how this decoder needs to do its generation, at the very first initial time step, it just gets the last hidden state output of the encoder RNN. So we're basically expecting that everything that the decoder needs to know to generate its translation, that the encoder is capable to stick the complete input sequence in like a hidden state representation and going, here decoder, good luck. Right? For longer pieces of text, that will break down. We can do this on the sentence by sentence level, right? You can cut up our text into sentences, and then it works relatively well. For a long time, if you look at Google Translate and so on, this is the model that they were utilizing for that. But it's still a little bit limiting if you'd really think about working with large prompts, let's say, and working with large text completions. But it's a bit unreasonable to think that we can hence encode all the information about a very long sequence into a single state vector. And yes, LSTMs can help us a bit there, and feeding it backwards into the encoder can also help us a bit there and so on. But at some point for longer pieces of text, this breaks down. This is not yet like a GPT-2 that you would get out of there. So a new model got proposed, which is based on calculating attention scores. A way to fix this problem of having to encode everything into a single hidden state representation to give to the decoder. And this is basically what the transformer model then arises from, but not initially. At the very first step, what people were doing is they were combining the idea of attention scoring together with this sequence-to-sequence model based on RNNs. Okay, what does that look like? Let's take a look. So this we already know. We have word2vec, GloF, fastText, and so on. Let me skip a little bit to the sequence-to-sequence thing. So here, this is kind of the old approach, is we say, okay, encoder, you get she is eating a green apple. At every step, you update your context vector, right? That's the name that's being used here for the hidden state vector, same thing. We take the context vector once you have seen the complete input sequence, and we give that to the decoder as its initial hidden state, together with a start of sequence input, and then from there, we have it generate until we reach an end of sequence. Drawback, if this blue thing gets very large, basically the decoder can never see what was part of the input sequence anymore. It needs to do everything based on this number of vectors that it started from. So for longer pieces of text, that's maybe not ideal. So yeah, you try to make the context vector length larger. That is something that you can do. You use an embedding layer if you start with one hot encoded words to convert them into an embedding, so you stick that in between as well, but still the translation of long sentences will be problematic. So attention is kind of our saving grace, and this reduces the fact that we need to be dependent on this single context vector to do our generation from, or to do our translation from, to do the decoding part from. So early approaches came or arrived in 2014, mainly for translation, and 2015, which started to introduce this attention-based concept together with RNN. Okay, what does this look like? I hope that I have a better picture than this one. Yeah. So what is the difference? We are not going to only just pass the last hidden state of the encoder as the initial hidden state to the decoder. Instead, what we do is, if we take a look at this picture again that we had here, the encoder already generates a hidden state after having seen the first input I. It then updates this when having seen the second input. It then updates this when having seen the last input. Okay, to start with, we could say, instead of just expecting the encoder to dump everything in this last hidden state representation, why don't we take all the hidden states that we got for each time step in the input sequence and give them all to the decoder part. So now if I have I like cats, I'm not going to work with an LSTM because then I need to write H and C every time. So I'm just going to say, well, this is H times step 1, H times step 2, H times step 3. Before we said we just take this thing and we give it to the decoder. Now as a start, we can say, well, take this whole thing and keep it around for the decoder port. So at least a bit better, because then I have a hidden state after every time step that I encountered for my input. Okay, what's another thing that I can do? The decoder will also become a little bit smarter. Before producing its output, since it's now seeing all of the hidden states, it should preferably try to learn how to focus on specific parts of this input that I have, depending on where it is in its generation process. And that's exactly what attention means in this case. Attention means that based on where I am in my output process, that I will calculate scores. And again, you can kind of feel probably something that I'm going to multiply, that I can calculate an attention score for each of these hidden states, and hence make them more or less important depending on where I am in my output sequence. That's what I would like to do. Becoming less important basically will mean that I have an attention score which is close to 0. Being more important will mean that I have an attention score close to 1. So probably the way how I calculate these attention scores, what I can already kind of feel is this will be the result of a softmax of something that I do. Because that's how I get something which is between 0 and 1. So how is this done? I have the orange things. Those are my hidden states that I have made there. What do I also have? Well, my decoder is busy somewhere in its generation process, has maybe already generated a couple of words, right? So I also have the hidden state of my decoder at this current time step. It has just, so for the decoder part, remember that it got like the previous inputs that it generated at the very first step. This was start of sequence, right? It also gets like an input hidden state. It's producing an update of its hidden state, and that hidden state, or I can draw it like this, is also utilized to softmax me the next word that it should generate. So I currently have its last produced hidden state as well for the decoder. That's the purple thing that you see here. Now somehow, we don't know how yet, but somehow I'm going to utilize these inputs to then calculate a score for each of these hidden states, each of these orange parts. And I don't like that it's 13, 9, and 9, so buff softmax them so that they're between 1 and 0. And then the rest is simple. Multiply the scores, like I said. These two guys at the end become less important. And then, yeah, what do I do next? Let's sum them. And then I get like a new blue vector. It's a type of context vector again, which I can also give to my decoder to produce its output at this current time step. And this blue thing, of course, is now also going to differ depending on how I calculated these attention scores, right? Okay, altogether, what does this look like? Well, you can then come up with a model that looks something like this. What happens here? My encoder is done. Once this thing has produced its matrix of hidden states, I just take this thing, I can forget about the encoder part. Other than that, there doesn't change a lot there. I start with now an initial kind of hidden state vector for my decoder part. Yeah, I have to do that because I can't just give like this whole matrix now. So now here I need to initialize this thing with, again, like an initial hidden state. I'm not just passing the vector directly from the encoder like I did last time. And I'm also starting, I'm giving it an input. Here it says end, but this is basically the start of sequence token. It's just saying, okay, start your generation process. What I will do based on this, well, somehow I want to say I have this hidden weight matrix, right? I have this initial state. Using this, I compute some attention scores, which I multiply with this thing. I sum them, and I get this blue context vector. My decoder updates its internal state. That's what DRNN does anyway, right? So it updates its internal state, so to produce an updated version of its hidden state. And so I'm using this thing together with this matrix to calculate attention scores, multiply them, sum them to get a context vector. And then what I use in my downstream task is to say, well, take this context vector together with your updated hidden state, which normally I would only use the purple part in my downstream task. Now concatenate the context vector to this, put your preferred MLP stuff on top of this and produce a one-hot encoded output I. And then you pass this thing, just like we did last time. Here you get another hidden state update. You use this hidden state to calculate attention scores. They will be different there. You will get a new blue vector that gets concatenated, M. So depending on where you are in your output, depending on what your updated hidden state looks like currently, you will get different attention scores and hence a different context vector that pays less or more importance to a specific part of the full input sequence hidden states that you now got from the encoder. If you visualize these attention scores, because we have for every output step, we have different attention scores and we have a score for each input that we got. We can kind of then look at what these scores, what they look like. And we have a sentence here, it was French for the input sequence, and it gets translated to English. Well, depending on what the word is that I'm currently generating, these attention scores pay more attention to the hidden states which are part of the input. And then you see that, for instance, here, the European Economic Area, La Zone Économique Européenne, that it has learned to say, yeah, but my first word that I'm now producing is D, that still matches with the particle in French, but the next word that I want to generate, or that I am generating or going to generate, is European. Why? Because these attention scores have learned, careful, pay more attention to this hidden state than to this hidden state. So give this one now a higher importance. All learned, yeah, how does it do this? What we didn't know yet is okay, but then where do these attention scores come from? We use this purple thing, and we use this orange thing, and from there we get this pinkish attention score thing, but how? Right? How does it know? Well, again, it will boil down to utilizing some sort of parameters that are partly or that are jointly learned downstream. So how do you calculate attention scores? Well, you have different suggestions that have been made to do so. The thing that's being utilized in most cases nowadays is just a scaled dot product. So just a dot product between this S thing here and this H thing here. And what are these two things? Well, on the one hand, we need to calculate scores given this orange thing and given this purple thing that we have here. In more general terms, what this thing actually tries to do is it says, okay, if you look at this formula, this dot product here, and forget about the normalization here a little bit, you have a query, and think a little bit in Python if you use a dictionary, and you know that the dictionary has keys, and you can ask the dictionary, please, given this key, give me the value for that key, which is in the dictionary. Now, in Python or in programming languages, if you have a dictionary of keys and you want to get a value for a specific key, you need to be very exact in the key that you ask. If the dictionary contains the key A, you need to ask for A and not for something else, otherwise it will say, well, this is not in the dictionary. What we try to do here is to make some sort of a soft dictionary where we have multiple elements in the dictionary, each with their key and associated value. And now you come along and you say, well, I have a query here that I want to match with these keys, but it's not an exact match. It's kind of a softmax. And it's kind of a softmax, indeed. Give me a distribution of weights over all of your values that correspond well to the query that I have here. That's basically what I'm doing here. So if I look at what are the keys and the queries and the values here, the query is, what do you want to look up? That's the purple thing, the decoder hidden state at this time step. What do you want to match this purple thing with? Well, the orange things. So the keys are all the vector representations that my encoder has produced, all the encoder hidden states. Okay, then you get your score distribution that you need to multiply with your values. What are the values that you multiply these attention scores with? Are also the orange things in this case. So in this case, the keys and the values are the same, right? So I calculate my softmax attention scores basically by taking a dot product between the query and the key. And then I calculate my scores by multiplying the score that I get times the values, but here the V turns out to be the same as the K. And this is how I set up my architecture. Now the next step then is, okay, you can make stacks of using multiple encoders and decoders and make this bigger and bigger, and it becomes a bit more cumbersome to follow. But all of the recent models that we saw, BERT, Roberta, DistilBERT, all these BERT guys, and also GPT, they all make use of self-attention. And self-attention meaning that both your queries, your values, and your keys all come from the same set. Interesting. Here we already had the values and the keys being the same thing, but the query still came from somewhere else. And in this setup, the query was still something that was produced by a decoder or an M. So it's not really part of the same set that I have here. What makes the usage of attention now possible to create a transformer model out of this was proposed by the paper Attention is All You Need in 2017. And that paper said, yeah, but wait a second. If you look at this thing that you have just made here, do we still need RNNs here? Isn't just this attention mechanism on itself sufficient? Do you still need a recurrent architecture to do this sort of thing with? And this is what this paper proposed, said, well, you know what, forget about RNN, because it's also costly. In training, you need to run through the whole input sequence. It's hard to parallelize this. So do we need still this RNN part, or is attention itself, is that sufficient to do like sec-to-sec generation with? And that's what this paper found. Basically, it says we can take another approach. We have weight matrices that we're going to utilize for K, Q, and V, and that we will utilize to derive key, query, and values. We will calculate attention scores using the same dot product or any other attention score, but we have that dot product, so we calculate attention scores like we did before using Q and K, exactly the same thing as what we did before. We apply softmax to them, we multiply the scores with our values, and we sum all of these to again get our output attention value. So it's exactly the same thing as how attention was working before, except that now we're saying, but we're not going to do it with recurrence anymore. We're going to do it through some other mechanism. So we have weight matrices that we will utilize instead. What is going to be the basic idea? Well, both Q, K, and V stem from the same thing. They all come now from the input sequence that we have, the full sequence as a whole. We're not going to recurrently go through there anymore. We're just going to say you have a sequence of words, and you have one matrix to convert this into a bunch of queries, one for each input value that you have, a bunch of keys, also one for each input value that you have. That's still the same as what we did previously, right? So the k part is still the same. And also a bunch of values that you have, except that now the keys are not produced by an encoder anymore because you're going to kick that out. So we're not putting hidden states coming from an RNN in K. We're just going to multiply the inputs with a weight matrix, and that's now how we get this orange thing, this orange matrix that we had before. For the values, right, before that was the same as that orange thing. Now we're going to say, now, no, take a different W, multiply that with your inputs, and now you have values for each of your inputs. So your values now, these V's, are not the same as the vectors for these different K's, right? The name self-attention is maybe a bit misleading in that sense, that you might think, these are three the same matrices that we utilize. No, they are different because the weights are different, but they all are calculated on top of the same full input sequence. I remember the input sequence was word 1, word 2, word 3, word 4, right? And the query now doesn't come from a decoder hidden state anymore. Also now just simply comes from a weight matrix that we multiply with the input. So we get a query for each step of the input that we are at. Okay, what do we then do with this? Well, then we can go for a setup that looks like this. We have an input sequence, I love cats, right? Why are these green things not one-hot encoded? Because maybe we have already used word2vec or something else, but whatever. For each word in our input sequence, we have something that has a dimensionality of 4 numbers long, or we use an embedding layer or whatever to learn this directly. We have a representation, 4 numbers for each word. Our input sequence is 3 words long. We're not going to use recurrence, and still we're going to claim that, but still this is a thing that can handle variable length sequences. So then how does that work? Well, we apply the same kind of basic setup that we just introduced. So yeah, step number 1 is we apply these WK and WQ and WV to get for each input step, to get a key and a value, a key and a value, a key and a value. That's just based on this weight multiplication. These weights are trained, part of the whole thing, and we get this. We also get a query, and typically there we choose to only use the query representation of the last item in our input sequence. And then we can utilize the same approach that we did previously, where you utilized the dot products of, remember, the key and the query to get a score for each of our input elements. So this is the attention score associated to every element in our input. Already softmaxed, so we don't really put that as a separate step anymore, so these blue scores have already been softmaxed as well. Remember, last step in our whole kind of attention score stuff, we just follow the same thing, right? We then multiply this softmax score for each of the values that we had, right? So we get this yellow thing, and this yellow thing. The idea is then that we, again, our last step was we need to sum them together, right? In the previous picture, that was this thing. We convert now all of our multiplied score values, and we sum them together to get like a singular thing, and we get a singular output there. And then the idea is that we can utilize this output in a downstream NLP network as we did before, and then have it generate the first word of our translated sequence. But what do we do next? That's just the first word in our translated sequence. Then we do the same thing over again. We take a new input sequence consisting of the input sequence plus start of sequence plus the first word that you just generated, and we do the whole story again. We apply the same weight multiplications. We calculate new attention scores for each of the inputs. We take the last one here with this query. We pass it down to a downstream MLP, and we have it predict the next word in the sequence. So it's also autoregressive in that sense. But no recurrence anymore, because we just work on the complete input sequence as a whole. The reason why this works is because it doesn't matter here how long that this input sequence is or becomes as we are generating text, because we're just doing the same thing for every element in the input sequence. We're multiplying it, but in the end it gets summed together anyway, right? So that's the idea that makes this work. Benefit is that you can easily train this in parallel. You don't need to run to your input sequence one by one. You just give the complete input sequence as a whole. Drawback is that as you're generating, if you now use this thing to make a translation or to generate text, is that, yeah, auto-regressively, this input sequence becomes longer and longer and longer as you generate, right? You start, I mean, if you think about something like a ChatGPT, first this input sequence would be the prompt that you gave it, and then like some start-off generation token added at the end of it. ChatGPT generates its distribution over the next tokens that it thinks are good to use as an answer. Well, we pick one from there, we stick that token in the input sequence, and we do the whole thing over again. So here you see how this scales exponentially depending on how long that your input sequence becomes. So in inference, this is what causes transformers to be quite costly. You can train them very well, but in inference they are quite costly, especially if your input sequence becomes quite long. You can then add refinements such as, well, why one attention score? Why don't we calculate multiple attention scores? Okay, well, fine, then you just have multiple attention heads that you stick onto this and that you utilize in some way. What is also a drawback here, which the recurrent architecture does not have, but also a drawback here is that this thing basically doesn't care if I give input 1 and input 2 here, or if I would swap these two words around in the input sequence. The order of the words actually doesn't matter here, because for every input word separately, it's calculating keys and values and an attention score, and at the end we just sum these things together. Right? We're trying to stick everything into this last word by this query mechanism in here, but here the order between these two guys doesn't really matter. Now, typically for generation tasks, it's quite important that if I give you an input sequence that you have some mechanism of ordering in there. So to fix that, what we typically do, or what is typically done, is that we do not just give a representation for the word itself in the input sequence, but we also give a representational vector indicating the position that this word has in the input sequence. And you might think, aha, that is just 1, 2, 3, 4, 5, 6. That's the best representation that you can get for there. Yeah, but again, you're dealing with variable length input sequences. In training, maybe you've only given it input sequences up to length 100. Now the user gave you an input sequence of length 200. It's not going to know pretty well what to do with these numbers 100 to 200 there. So instead, we need to basically convert integers that denote some kind of ordering into a representational vector for that. A representational vector to give like an ordering, to give like a sequence numbering representation. And for that you have positional encoding approaches or rotational encoding approaches, which basically look like this. This is an encoding in 4 numbers for what is the first word in a sequence, and this is for the second word in a sequence, and this for a third word in a sequence, and an encoding which is more stable for this architecture to utilize. Looks like this if you visualize it. Basically the dimensionality is in the y-axis, and then the sequence number that we convert. You see that it tries to retain some kind of structure in that encoding as well. But this is the mechanism how a transformer model knows the position of a word in that input sequence. The recurrent neural network knows that intrinsically because we just let the words arrive one by one. Here we need to mix that in with the information that we have. So altogether, it starts to look a little bit like this. Things that we didn't discuss yet is there is a layer normalization that gets stuck in there as well. There are adaptations where you can throw away a piece of this and only work with one port. That brings us a little bit too far. But the whole idea is we just calculate attention scores on the whole input sequence as a whole, and that's what we use to generate the next output. And this whole recurrent mechanism, we don't need it. And that's the attention is all you need kind of idea. There are many other variants, like of course the GPT models are the most well-known today kind of instantiation of this idea, but also approaches such as Elmo. Basically at some point in time we were in the middle of utilizing RNNs, as you see here, with attention, and then slowly realizing that these RNNs are actually not necessary. But also sometimes like nice ideas like using bidirectional setups or learning different representations for a word depending on the context that it occurs in so that you can better know that stick has multiple meanings depending on where it is utilized. But all of these are basically older ideas of the same thing, trying to mix attention with RNN-based mechanisms before GPT came along and said, well, you don't need the recurrent part. You can just do it all with attention and just scaling up your model to be enormously large, and that seems to be good enough on its own. The initial GPT models, things like GPT-2, they were trained on text completion. You gave it a text like, hi, how are you doing? And it would complete the text as, I hope this email is finding you well. It was not really conversational yet. What made the jump from then taking this thing, which is good at text completion, to become more conversational is all in the training data. And it's basically things such as instruct tuning, where OpenAI said, yeah, but wait a second, if we now have something that's very good at completion, let's first train a thing on all the language that we have, just to complete language, so that it understands language very well. And then we're going to make another data set to further train this thing, but there we're going to introduce special tokens in the data set, tokens that indicate, well, this is something that the user is saying. How are you? End of the user part. And then you, or agent, and then in your training data, you say, well, what I expect you now how to complete this text. I am fine, how are you? And then the next time that you want to have this thing behave in a conversational way, instead of asking it to complete the text, how are you, on its own, the user sends this to you, you just say, I'm going to stick this in the special end of user and beginning of user tags, and then start of you, same model. And now suddenly it behaves conversationally because it has learned from the training data that if text is surrounded in these special tags, that we're more like having a conversation rather than text completion. Many of the new tricks are all based on still exactly the same idea, trying to play with tokens in this vocabulary and the way how you set up your completion. The next big step was then, so this is typically called supervised fine-tuning or instruct tuning. Next step then is reinforcement learning from human feedback, which is reinforcement learning, but it's quite simple. It's basically saying, well, and now I'm going to adjust the weights by having the model generate 2 versions of its completion. How can that be done? Isn't this deterministic? Well, no, remember, I get a probability distribution over the next tokens that I could take here to predict. I can sample from there, right? With some amount of temperature. I don't always need to take the highest predicted one. I can basically mix a bit to create text which looks a bit different. So generate 2 different versions of the same kind of prompt and have users tell you, which one do you like most? I like this one most because here the model, it's a little bit more friendly to me. Okay, then we will utilize this to update the model again a bit further. So then you have reinforcement learning from human feedback. The next step is that you start to play with chain of thought prompting and in-context prompting, where you start to figure out, hey, if we also start to stuff in additional secret text in this prompt, things such as you're an expert on machine learning, that the model starts to generate better completions. Or if you do not do well, you will not get a tip, but if you do well, we'll give you $100. It does better in that case, right? And then you can start playing with tricks such as, before you answer, first think a little bit internally and first generate a plan. And we're not going to tell the user what you generated, but we're then going to feed that back in onto yourself and saying, hey, this is the plan that you just generated, now produce your final answer. And then you have like these reasoning mechanisms that pop up. And you can then start playing with additional thinking tokens and system prompts and so on, but it's all based on kind of the same mechanisms. Then making models multimodal. Same thing, also transformer architecture. Now you have images. What do you do with them? Well, an image is a sequence if you think hard enough about it anyway. Just cut it up into small patches and just feed all of them one by one as part of the input. And on the output side, let the model choose to generate either textual tokens or image tokens. And then for the newest approaches, you can use like things like flow modeling or diffusion models to make that even better. But that's basically the initial ideas. Things such as a vision transformer just says take an image and cut it up into a sequence of patches, and we feed that instead. So we're still kind of stuck with this stuck. Well, it works well enough, but this architecture is already pretty old by now. All of the newer kind of things that we're doing, a lot of it is part of post-training, where we start with baseline transformer models that we already have with either 30 billion parameters or whatever, and trying to perform reinforcement learning approaches to make them better at reasoning tasks and so on, or make them more aligned with user expectations. But the baseline models have been more or less the same, except for kind of smaller trials that mix in diffusion ideas or that try to mix in state space models. But of course, if you're a large company trying to make your models more multimodal, that you can just directly upload video or PDF files or audio or whatever, of course, this is currently the way to go. If you can still utilize your current architecture to do that, and you're close friends with NVIDIA, and you have 1,000 GPUs in your data center, why not, right? So these models become, on the one hand, larger and larger over the years, but like we have already seen in many cases, there is also this push towards quantizing models and making small versions that also do well, also from kind of this realization that it would be fun that we can run LLMs just on our local machines rather than having to go with one of these big tech giants. So this is like a continuous fight that's been happening. And like I said, the vision transformer for more than just text as kind of a complete alternative to both convolutional neural networks, but in many cases also to more diffusion oriented based methods where we just take images directly and we cut them up into patches and we just take them as an input sequence and we ask a model to generate an output sequence of image patches. And that seems to work relatively well. If you go into things such as video generation, for instance, yeah, then we really go off the rocks. Then you do start to see that for specific frames, you might have something like a diffusion model to generate every specific frame, but then to keep the frames coherent from one to the other frame, that's still being handled by a transformer-based model because that tends to work better with sequences. So then also there you do see to start combinations of these different approaches to get like that world model aspect high and that video generation aspect high. And then if you want to also feed in your input things such as, but the person should be posed like this, or it should start from this image and end with this image. Very similar underlying architectures, but just the scale of training gets exponentially larger and becomes, of course, heavily more or increasingly more difficult for just like standard practitioners or hobbyists. So in that case, yeah, we use baseline models or pre-trained models, and we try to utilize those. There are a couple of other tools that are mentioned here, like GenSim, Word2Vec, GloF, FastText is implemented in there. Also has topic models in there as well. So for that, GenSim is kind of a good thing to utilize. Things like Ellen NLP, Spacey, Rasa, named entity extraction and things like that. But to be honest, in most cases, you would just take your favorite LLM instead. Hugging Face, hence has models. Vader Sentiment is a pretty easy to use sentiment analysis tools that tends to work well on social media. But for the majority of cases, take like a pre-trained model. And it doesn't always need to be something which is enormously large. Even like in the BERT family of models, these still get utilized a lot to generate good document embeddings and good sentence embeddings that you can then just pass to like a smallish neural network down the line, or you can stick even in something like an XGBoost, and also tends to do not too badly. I think I already mentioned it, but in Python, sentence embedding, you have sbert.net, for instance, that does this for you, and you just pick like a pre-trained transformer model, for instance, from Hugging Face or somewhere else, a mini LM, something which is small, and you just say, okay, I have a couple of sentences, and I want you to create embeddings for these. Well, here they are, and then you can just utilize these as feature vectors in like your XGBoost or something like that. And that tends to work not too badly in the majority of use cases. Again, for practical cases, it's always a bit more experimenting and work than this makes it appear, but this is kind of the approach that most people take nowadays. Good. Maybe a final thing, something that you will not have seen me do today. It's like, a lot of visualization. I might already have mentioned it in the visualization session, but do be a little bit careful with this kind of, at some point it was very popular, these kind of word cloud based approaches to like visualize text. Well, your word cloud is always going to show the most frequent English words anyway as being the most important words, so you will have to do some work in terms of cleaning that up again. And very often, yeah, just a word cloud is not very revealing, especially not if you have like a label there anyway, like a review sentiment or like an outcome. So this is a tool which is like a little bit nicer. It's also from Spacy. And they just use a scatter plot to do that. And here they take all the words that appear in speeches by Republican and Democratic presidential electives, I think, or maybe presidents themselves, with the axis indicating frequency, and then basically with the position being closer to Democratic frequency or Republican frequency, or both or none of them. And the nice thing here is that rather than a word cloud, which would just show you the top right here of this image, that you immediately get like it's actually the bottom right and the top left parts, which are more interesting because these are the contrasts between these two groups of text, right? It can be informative to know, this is what both parties are talking about a lot. They're talking about better success, Obama president, but it's especially in the parts how they differentiate with one another that can reveal already a bit more insights. So also if you're thinking about like small visualization things, very often visualizations you want to show like contrast between things rather than just overall frequency, because you get the expected things, yeah, American, Obama, president, and better, and success. Okay, great, but every president is going to try to talk about this. So also this is a nice tool that I also always like to recommend. You can make this yourself in Matplotlib, obviously, but it's just as an idea, like think also a bit from the visualization angle and not just always show these word clouds as well. Good, that's it for today. Later tonight, assignment 4 dataset will be posted, and I will see you all next week for graph learning.